single column using this format where I specify the dimensions, this will give me the vector, and I should be able to plot it. So here, let's clear all the plots to show that I'm not showing the same one. Here, right here, it will show this plot right here. And you can tell because you see that the labels change. So this is a funky syntax with R, but yeah, if I only specify one column in this format, then it does give me a vector. So a recap on how to get data from a table. So a table is 2 dimensions. So I can filter data column-wise by, let's say, specifying the column names or the index of the column that I want, and also filter data row-wise. So to separate the 2 filterings or the 2 subsets, I have this comma separating out the 2 dimensions. So before the comma refers to the rows that I want to filter. After the comma refers to the columns I want to filter or specify. So here, when I happen to only choose one column, it will output me a vector. So that's so both of these will give me the same type of data that makes it easy to plot. All right. So yeah, we can use this plot in our render plot function. Let me reshape all of this. It's easier to see. Render plot. In this render plot, I just need to plot my data. And then in the main panel, I need to have an output plot. So here, I have the sidebar layout. I didn't specify anything in the sidebar, and I have this plot right here. Also, I can change the X labels, X label as CTY, Y lab as highway, and then the main will be paste Y. So to concatenate strings together in R, you do so using this paste function. In other languages, you might think, oh, it's simple to combine text together using the plus symbol. But in R, it is different because everything is a vector. Adding strings using a plus symbol will work out in an unexpected way. So to concatenate strings together, we use a paste function. Okay, and then the separator, something like this. Let's run this. Okay, so city versus highway, we have the city miles per gallon versus the highway miles per gallon. So yeah, having a static plot, not very interesting. So we want to be able to have some inputs that allows us to select the type of data that we want displayed on the plot, right? So what if we don't want to compare city miles per gallon to highway miles per gallon? We want to compare other numeric values. I can use a type of input. So let's see. Input. So I can use this select input to allow me to select a value from a list of other values. So what I want to use for the select input is to choose a column name to use to display my plot, right? Or to choose the data I want on each axis of my plot. So here, in the select input, I need, of course, an ID for the input. So let's just call this X. And then the label will be X. And then I need the values to be able to select from. And the values that I want to select from are the column names of this table. So the column names I can retrieve in a couple of ways. The names function will give me the names of the columns. Also, there's a function called call names. So that will also give me the names of the columns. So it doesn't really matter which one you use, names, MPG. One thing we could do is we can have a variable saving that information so that we don't have to keep calling it, MPG, and then refer to this later on. So fields, and then we can have a default value, the selected value, and we'll say city miles per gallon. And then for Y, we'll have highway miles per gallon. Okay, and then we'll run the app, see what it looks like. Here we have our two inputs. Obviously, I didn't connect it yet with the server data, so this doesn't work. So now I need to connect it to the server data. I need to be able to retrieve that value and then put it in to filter my data. So here, using this $ symbol, I'm not able to easily input text. So we'll use this format where I have this square brackets with a comma separating the dimensions. This will be the input X. Okay, this might look a bit messy, so we'll just do something like this. This will be input Y. Okay, that looks good. Same thing here. The labels must change as well. Then I can run this application and then choose the different values that I want to display. Obviously, not everything is numeric, so this is not going to be great, but the concept is similar, I guess. So yeah, certain columns that you select, because they're not numeric, you're going to get an issue trying to create a scatter plot from them. But yeah, most of this is not that interesting. Okay. Besides creating the plots, I can also output the data itself so that users can take a look at the data from the table. So let's see. I need to have an output storing that information. So output data, and I want to render a table. And in this table, it will just be the data set. So if I run this, oh, right, I have to define the retrieval of it. Table outputs. And this will be data. So usually the correct output name associated with the render name will just be whatever it is that you're trying to, well, this part will match for the output and the render. So here we can reload this. And then if I scroll down, I see all of my data. It might not be ideal. Oh, yes. So my email is rh3220@columbia.edu. Okay. Yeah, so for those who have to drop early, this is my email. So here, I have, yeah, so if you do need to drop out early and you don't retreat, and you want the notes, please email me and I will send you the notes. So most of the time, the data that you have, it might not be this small, right? Where I have just a couple hundred lines. You might have data that are millions of lines. It's not ideal to show all of that on a web page. You'll crash the web page with the amount of data that you have. So what you could do is you could limit the amount of data shown. And we can control that using another input. We can have a numeric input. Slider input works as well. But there are many different inputs for different for different types of data. Rows, number of rows. We take a value, and then value is equal to 5, a default value. And then we can use this with this head function. So this head function allows us to subset our data set from the top, choose how many rows we want to output. So I need to specify the data structure and then the number of rows that I want outputted. So if I reload this application, here I'll only show 5 rows. And then I can click up and down to display more or just type, and this will display more. Another way we can render data, or a nicer formatted way, would be to render a data table. So this applies nicer formatting. So data table output, data table. And then we can have, this section right here below, this will be the data table output. You'll see it has a lot of features already provided to you. You can select how many data points to show in one page, and then you can go across different pages. You can do filter sorting as well. So data table may be a better way to display your data. So you do have options. Okay. So yeah, let's move on to the last app that we're going to create. And this time we'll be looking at a more interesting data set. So the library that we're going to be using to get the data is called QuantMod. QuantMod. So please install this if you don't have it. And then once you have it, you don't need to ever install it again. So you can comment it out. Library, QuantMod. So in this library, it provides a function that allows us to get daily stock information for companies. So we can use this get symbols function that allows us to retrieve data from any company, publicly traded company, for specific time periods from, let's say, 2023 01 to 3. What day is it today? 10/6. But here, if I run this function, I can get the opening price, the high price, the low price, closing price, volume, and adjusted price for the company that I specify, the symbol, and for the specific dates that I specify in my arguments. So I think the from and to, they have default values. We don't need to necessarily do this. The auto assign set as false is just so that the data gets displayed. If we don't have it, then you'll see something different. You'll just see the symbol itself. So the auto assign is to allow us to get the data. Setting the from and to allows us to filter the dates. Otherwise, it'll just give us all of the data, which is something that you might be interested in. And the format for the date string is always going to be 4-digit year dash 2-digit month dash 2-digit day. So this is a common format for displaying dates in coding languages, or for referencing dates in coding languages. This is the more popular one. Always date, year first, then month, then day. So using this data, so the data retrieved is not actually a data table. It's actually a time series matrix, or it's not a data frame or a data table. It's a time series matrix. So it's because it's a matrix, all the data types are exactly the same. We have numbers as the data type, or doubles, I believe. And they do have names for each of the columns. You have Amazon.open, Amazon.hive, blah, blah, blah. And then the names for the rows are going to be the dates. So this is a time series matrix with dates as the label for the rows. So I can make a plot using this data. If I just plot, let's say, just one value, let's say data, run this stock data. If I only plot one column, I am able to get a line graph, specifically because this is a time series matrix. So because the rows have labels, it can then plot the rows or the dates as the x-axis for this line graph. And then the y-axis will just be the label or the data for that specific column. So the plot function is pretty flexible. You can put a lot of different data types and in a lot of different formats, and it'll figure out how to plot it. So here we are plotting some sort of time series. So now that we have our data, let's quickly create an app since I only have 10 minutes left. So to create the app, we need to have this text or the code for the app. We'll have a sidebar layout, sidebar panel, main panel. In our server, we're going to have a plot, of course. So let's say output plot, and then we will have render plot. And in this render plots, let's just say we will have this as our data, and then we can actually, for now, we'll just do something like this. Stock. So here we have our sidebar layouts, and in our plots, we have our stock data. So of course, it's not interesting to have no ability to change the plot. So we want to do stuff like allow us to change the symbol, right? You guys may not care about looking only at Amazon data, right? I care because I work there. But we can create an input to specify symbol, which symbol to use. And the value by default, Amazon. Okay, that's about all we need for now. Here, since we are changing the data that we are going to be using, this section of code will actually be quite big, right? We can use multiple lines. So for all of the code that I input into the render function, they've all been single lines of code, which means that whatever that line is, that's the output that gets inputted into this render plot function. But what if I have complicated code that I want to execute before I decide what I want to apply or send to the render function? To encapsulate a bunch of lines of code within a function, I can use these curly brackets to allow me to write a bunch of lines of code and then only output the last thing specified. Here, like this. So whenever you see this curly bracket, that defines a scope or a section of code where you can do a bunch of things, and then the last thing specified will be outputted. So here, we don't need this stock data variable. Let's get rid of this as well. Here, we will, every single time the symbol changes, input, we will redefine what the stock data is. And then once we redefine the stock data, we can then plot the new data. So let's save this, run the application. So here we have Amazon. Then we have, we can change it to Google. And then the data will change. And then we can have Apple. What's Apple's symbol? It's APL. So we have Apple, and so on, right? So another thing that we can change is the dates range of the values that I want to filter by. So what if I want to get all of the data from a certain, what if I wanted to change the range of the dates that I want to look at the stock data from? I can do so by using a date range input. Date range input. So a date range allows me to pick two dates, a starting date and an ending date. You might see this very commonly when you book trips, right? For train tickets or plane tickets, you generally have a departure date and a return date if you're doing round trips. So this date range input allows us to choose two dates. So we'll call this dates, date range. Doesn't really matter what we label it. Don't forget your comma. And then what was the argument? The start and end. Okay. The start we can set as 20230101. End can be we don't have to specify an end actually. We have default values for start and end. And then we can use them here. So input date. So this dates value or input that we have, because it's a date range, both the starting date and ending date are both saved to this attribute of inputs. And it's actually a vector of two values. So if I wanted to get the starting date, I just get the first value. If I wanted to get the ending date, I can just get the second value. Okay, if I run this, by default, if I don't specify an end date, that will just be the current date. And then I can pick and choose when I start, when I end, and so on. So what if I didn't want to just plot? So let's look at this data again. Plot this. What if I didn't want to just plot, let's say, the opening price? I should also include a label for this. What if I wanted to plot the high price, the low price, and the closing price for all the dates as well? I can do the same thing and create a bunch of these. Open, close, 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 I think is the fourth one. Close is the fourth one. Open, close, high. Low. This is 2, 3. So if I run this, I can now have all 4 displayed. So what you might have noticed is that instead of my data being displayed immediately, or my graph being displayed immediately, there is some slowdown with how the data is being presented. So if I change this, you might see a pause before the data reloads. So you didn't see this before when I was only plotting one graph. And the reason for that is that within every single plot function, every render function, I'm calling the same function to grab data. And it's actually the same exact data every single time, but I'm doing it 4 times. So 4 times as many times as before. And this is actually a bit unnecessary. This slows down your application by making a lot of unnecessary processing, by making a lot of unnecessary API calls to get the data and then to do the filtering and stuff. So because this data is actually reused in all of these components, I can create something that allows me to only retrieve the data once and then have that data be reused in all of these different components. And so what that is that's a reactive. So let's say I create this stock data and I create a reactive from it. So what that means is that if I define the stock data here as a reactive, you can delete all of this. I only have to make one API call or one function call for this get symbols to grab all the data, and then I can reuse that information in all of these other different functions. So once the symbol changes or the date changes, only this part or this stock data gets retrieved once and then can be reused in all of these other sections, in all of these other outputs. Whereas opposed to what I had before was that once the inputs, the symbol inputs or the date inputs gets updated, all 4 of these plot functions call the get symbols function to retrieve data and then plot it. So instead of making 4 calls, I can make 1. So that makes it a lot more efficient. And to retrieve that data, because it's a reactive, it's actually not, you need more than just the variable name. I need a parentheses after. So it's actually a function call. So the reactive creates a function called stock data that allows me to retrieve data every single time one of these inputs gets updated. So here, it's much faster. So if I were to click something else, it does show up a bit faster. Doesn't look like it's that much faster though. Okay. And so here you have it show up a bit quicker. Let's see. So what if, would you mind sending me a copy of R6 today? Yeah, can you email me later? Okay. So yeah, I am going a little bit over time, but so this is the okay. So here, this reactive is very important so that we minimize the amount of processing that we do. So we don't have to call the get symbols function 4 times, then just do it once and then apply that data elsewhere. What if I'm in the middle of changing these values, but I'm not done filling in my filtering criteria before I choose my data or before I want to plot the new data. Right now, all of my data gets refreshed immediately once one of these changes. But what if I want to take my time in choosing the dates I want, choosing the symbol, and I only want to retrieve data whenever I specify it? So I can do that with an event reactive. Events. And what this event reactive will do is that it will detect a single change in something that I specify, and then only refresh the data after that one indicator gets changed. So what I can do is I can create an action button. Button. Data. That allows me to see, so I can create an action button that allows me to wait until the user clicks the button to retrieve the data. So what this does is it's just a button, and then in the server, this event reactive can detect when this button has changed. So basically, whenever a user clicks the button, I then can retrieve new data. So let me save this. So in the beginning, you'll see that no data is shown because nothing has happened to this refresh data button. But once I click it, I now have my graphs. Here, if I were to change the symbol and type in Google or change the date range, the graph does not update until I click the refresh data. So this is important to limit the amount of times that you retrieve data, especially if it's not necessary. And then the last thing I want to talk about is another type of components where we can display these plots. These plots, we have a bunch of plots. It's kind of annoying to have to scroll through the web page to see all of them. So there's another component or a layout that we can apply to display all of these plots in a much nicer way. So here we can use a tab set panel, which will create a bunch of different tabs where I can switch between them to show different things. So here I could have a tab panel called open, and then I'll just copy and paste what's going to be inside of it. One for close. high and one for low. Okay, reload this app, refresh the data. Now I can just alternate between the different tabs to show my graphs. And yeah, that's about it. I have gone quite a bit over time. So let me quickly save this and share these documents in the chat. Okay. So yeah, are there any questions? If not, or if you have questions later, feel free to email me for your questions, or you can ask them now. I'll stay for another 5 minutes. We have a hard stop at 10:45. Next week, I think we are going to be going more into data visualizations, I believe. Might need to check. Yeah, so next week will be more about focusing on data visualizations. That is a pretty powerful tool in R. Thanks.
Professor.
Yes.
So in my art studio here, like just at the first beginning for the data part, it's not showing in the global environments. I have installed the package already.
Yeah, can you share your screen?
Uh can can I share like this? Let me see.
Did you save the
Mm,
so you're using a different
yeah.
okay.
Do you want me to switch? I
No,
can
no, it's
switch.
fine. I can let me just ask you a couple of questions.
Yeah.
So this is for the stock app, or what are you which app or which data are you trying to show in your environment?
The Amazon data, like
So
overall.
here, let me share my screen then.
Yep.
Uh, so you see my screen?
Yes.
Okay. So for the Amazon data, it
Mm-hmm.
doesn't show unless you define a variable storing the Amazon data. So you can, if you were to just run the function like this, and you type in Amazon. Oops. Oh yeah, let me clear this environment. So I don't need these. If I were to just run this, sure, I see the data in the console, but
Wait,
it doesn't
how do
show
you
any.
run this?
Oh, I can do control or command enter.
Command enter.
Yeah,
I'm a MacBook, so I do
yeah. So
command
command
enter.
enter. MacBooks have control as well, but yeah,
Oh, yeah. It's showing.
yeah,
Okay.
command enter will work. It's more convenient, probably. So here,
Okay.
this does run the code, but I
Mm-hmm.
haven't defined a variable storing that information. So if I
Mm-hmm.
haven't defined a variable, then it won't be available in my environment. So I just need to set some variable equal to it. And now you'll see that it shows up. So you might probably have this code, but you never assigned it to anything. You didn't save it.
Oh, yeah, yeah. Yes. Okay. Yep. Thank you.
Okay. Anyone else? Not. Have a great day, everyone.
Thank you, Professor.
Leave it on. Okay, it's 10:45. There's no more questions. I will be leaving. Have a good day, everyone.
はい、僕こうやってやってるんで。いや無理あるだろう。
sure that we all have got the files we need. So let me just put them in the chat, the files we need, so you can start on already including these files in your environment. It will be the same files as last week, as I said. So we need the index file and we need the random walk file, and I put them inside our chat, and should be able to see them. All right, slowly getting started. We will start our collab session. We're just starting a brand new one. And same as last week, I will share the code at the very end. So we already, I already mentioned that there will be a poll. Please stay for the poll. It's just before the end where we can get your input a little bit. And then afterwards, I will share the code, everything I'm typing. What I'm trying to do today is after each session, just please give me a thumbs up, and I will ask you if you were able to follow or if you need bits and pieces of the code. Because what it does today is it builds up from the beginning of the class to the very end. And I will just give you a brief overview of what we're going to look at today. So we will start with whatever we did last week, very briefly. We will look at autocorrelation. We will look at how to assess autocorrelation and partial autocorrelation. So to see, how it works and what it can do. And then we're starting off with the models, with the forecasting model. So we have got an auto regression model, AR. Then we have got a model called, just go down. We will do a model after normalizing, we will do a moving average. Then we combine both of the models together, which is called the ARMA model. And then we will go to the ARIMA model. And if we still have got time, we will start with the ARCH model, which is a volatility model. So first, we're starting off with forecasting prices from indices. And then at the very end, we will look at the volatility. So I hope everyone is about to start, and I gave the files inside the message chat. So we need the following libraries to start off first. Let me just ping this one first in here. You can just copy paste it from there. I will do the same here. We'll run it. It will take a little while for me because I just restarted it. Do advanced. And today's date is October the 6th. All right, so we need a few lines down here. And I will copy as well now the everything or a summary what we did last week. So I can put this one in the chat as well. And I will demonstrate it on here. So for this one, we need the index 2018. And the file I already posted is in the chat. Let me know if you can't see it. So we need to include these two files. So we're uploading the files. I go to my downloads. Hold on, I've got somewhere here my downloads. And I've got the time series, and I need the index and the random walk. That's the two files we also had last week. We put them, I usually put them in sample data, move them up here. And that's the two files we need. All right, so the first part of the text is code is first we need the raw data, which is our index, and it includes DAX, FTSE, Nikkei, and S&P. For this one, actually, we're gonna use the FTSE, so we only will use one of these ones. as we already did is we set a time date, we put in it as an index, we set the right frequency, so we have got the right days, consecutive days. We fill the days which we don't have data with a ffill function. We generate another column called market value, delete everything of the rest. We generate DF, which is our training set. So that's the training set of the market value. And then we have got a test set. So we just run that. And the next one will be generating the two other data sets we want to compare it with. So let me just copy this one over here and copy it in here. So here we generating the data set white noise, and we putting in our data frame. And down here we doing the random walk, and I provided the file for the random walk for that data set as well. At the end, if you have done everything what I did, you do DF, that's our data frame, and you should be able to get a data frame which has got the date, which is the index at the beginning, the market data, which is the FTSE. There's our index. We have got white noise data set, and we have got random walk. So I just pause here for a minute, and please let me know if you have the same results DF here as well, because that's our starting point for this week's lecture. Let me know if you still need the file. I don't know if you can go back and see the files I provided. I'm happy to provide them again. And send the file again. Yep, I will do. No problem at all. Here are the two files. That's the two files. And if you could give me a thumbs up if you're able to get there. So we get the majority of everyone who is here is able to get to the point where I'm at the moment. All right, we have got one person already was able to get there. 2 person, that's good. Seems to work. Attribute error while executing it. I honestly haven't seen this one before. If you could just make sure that you took the exactly the same what I did, I leave it up here as well, and to see if you might have not copied over some of the text, because it seems like that you have got the files. The different object has no attribute date. Attribute date should be in here. So the data is here. It copies it over. Here you're generating the date. Underscore dot date. So that's where you're generating it. That should be the line where you're generating the date. And here the first one. So the next one will be then you set the index to the date, and then you set the frequency. So it might be somewhere around here where you have got the problem. Ping me very quickly if you still need time. Otherwise, I'm going to start the lecture today. And we want to get quite some exciting stuff. So first, Dickey-Fuller test. We talked already about last week about Dickey-Fuller test, sts.ad. Fuller df dot market value. Here you go. And this gives us the test itself. And then we can see that, you know, especially for the market value, we have got our p-value, we have got our observations. We can see if it is a stationary or not stationary. So it tells us with a 0.33, it seems like it's a non-stationary process. So just to test this one, we can do exactly the same with a white noise. So sts.ad folder test. Yeah. And we say df.wn. So that's our white noise. And there you can see that p-value is 0, is exactly 0. That's a stationary process. We know that white noise is a stationary process from last week. So we have got our market value is not a stationary process. We can do the same for the random walk. Let's just do the last one, sts.ad fuller random walk, df dot random walk, right? Random walk, here you go. And there you can see as well is our random walk is not a stationary process. It always, you know, it builds up to the last one, and it will establish a trend. What we did last week as well is we have got a quick look at the decomposition. So we can decompose our time series. So we say as underscore decomposition, we're using additive. And we say seasonal decomposition, decompose, df, market value, model. We have got two models. We have got the additive model, and we have got the other one, which is multiplicative, is deck additive. We want to plot it, dot plot. And as I said already last week, some of you might need plt.show to display the chart. All right, here you go. So you can see the market value. That's our first one. We can see how much is contributed from the trend. You can see that's not really any seasonality in there, and the residuals are, you know, not really that much of a effect. What I will do this week, I will also do a little bit of copy paste, so we can do the same with copy paste, just to explore if the multiplicative gives us a little bit more information on this. So just in the interest of time, I won't just type everything. I will just edit what we already typed. And this one here, this is just two different ways of generating our decomposition. And here you can see residuals are completely gone here, seasonality, nothing. So multiplicative gives us even less information for the chart. We're looking at. All right, so this is a little bit is seasonality. We can have got a look, as well as we can have got on the Dickey-Fuller test, we looked at stationary or non-stationary time series. So now we're looking at our new topic is auto correlation function, ACF. So that's, for this one, we will need another library. So I can just put this one in here, run this, and I can give it in the text box as well. And what it means, what does autocorrelation means? So there is an N missing. Anyone wants to join in and tell me what they understand of autocorrelation? I know that there's very different definitions, but what do you think? What's autocorrelation within a time series? Anyone? Anyone else got any idea? All right, you're probably still typing. What I understand on autocorrelation is someone of the variable itself. Yes, thank you very much. Thank you. So what you do is you have got your time series, and then what you want to look at is, does a time series at different points in time correlate among each other? Do my previous day to this day is highly correlated? Is the day before that correlated? Is, how much is the day 10 weeks ago correlated to my current value? So that's what we want to explore in autocorrelation. So for this purpose, we have got the stats library models, and we can explore that. So we can say sgt dot plot, and then we can say ACF. So that's our autocorrelation function. We take df dot market value. So we're just still working with our market value. We can define how many legs we want to explore. Do we want to look at just yesterday or the day before that, or do we want to go back 10 days ago or even 40 days ago? So in this case, we say legs equals 40. And then I think we need one more parameters, which says 0 equals true. I think that's one of the definitions we need there as well. So what it does, it includes 40 legs backwards. And false basically means that do not include the current period, because the current period is always one. Is if you comparing today with today, you always have got a correlation of 1 because it's the same. So this is why 0, we basically say it's true. So that means that we do not include today's date. Hold on. 0 equals true. We do not want to include the most current date because we know that it's 100% correlated. So PLT dot title, we want to give it a title. And we type this one first, and then later on, we just start copy pasting what we did in the past. So market value. And the size for me, 24 works that well. What I also want to do is PLT. I usually define the y-axis because sometimes it does a little bit strange things, and then your chart is very small. So in this case, I think I had got minus 0.5. That's my lower part. And then I have got 1.1. It's the highest part. So you have got a little bit of space on the top. And say plot dot show. So let's see how that looks like. We got a little bit of an error here. Plot show. Did I do PLT? PLT? Or do I actually don't need that for this one? Let's see. I don't need that. All right. So now we have to look at this chart and what it tells us. So here you can see that the correlations from one day to the other. So that's our legs. You can see 0 to 40. That's 1 day behind, 2 days, 5 days behind, 10 days behind. And then you have got here the factors of how much they're correlated. So what it tells us pretty much is all of the, it's of course, it's as further the days go behind, as less it has got an influence of today's date. But you can see here it goes pretty slowly down. So even the 40th day still has got a high correlation impact on today's date. What we also can see down here is these shaded area. So what we mean with the shaded area is it represents a significance. So if, let's say, these vertical points are within these shaded areas, it's not really significant anymore. So we will see later on, there will be charts where these points here, which are up here, are within the shaded area. So that basically means that they are not really have got any significance in impacting our current date. Values outside, of course, outside the shaded areas, they are significant, and they are different from, of course, zero correlation. Let's have got a quick look on white noise now. So we just type this one again, just for practice, just for practice, I guess. Plot, same thing as above. All we're doing is df dot white noise, lags, noise, comma, lags. We want to have got 40 as well. We want to have got the same as the 40 lags. 0 is going to be false. True, sorry. True. It's true. And plt dot title is ACF of white noise. Size, we do again, equals 24. And now we say plt dot our y-axis will be, and we put the y-axis a little bit shorter because we know already that it will change by not very much, I think. Let's see, 0.05, and we run that. Hold on, quick typo is GT. There you go. GT, plot.acf, okay. Plot underscore ACF. And here we go. Oh, we can actually, okay. So now I have to correct myself. If the 0 here, what I explained to you, that needs to be false. So we run this one again. So that's basically is when it's false, it ignores the first leg. So you can see it ignores the first leg. So you have to put the 0 as false. You can see the very first one is probably 1. So we're doing false in here as well. And then it looks much nicer, right? Yes, here we go. So now we can see how white noise is going to look like in our assessment of the autocorrelation. And here you can see that, there's not many points outside of these shaded area which we think are significant. And that makes sense because white noise is completely random generated, and the numbers among each other should not have got a significant correlation. We do have got some points which are a little bit outside here, but overall we can see that the majority of all of the points are within the shaded area, which means that none of the legs are actually significant to explain the current date. All right, let's do one last one. Is we do the random walk, so that I'm not doing so many typo errors. I can copy paste this one down here, and we can say that in this case df we only need to change is df, and we called it rw. That's our rw. We change the title rw, and then of course we have to change a little bit the axis. So we're doing 1, and we can do 1.1, and we run this. And then here we can see that random walk is similar already to our market value. It really depends on the previous values what the current value is, and you can see here is even less declining over the time period. So that's our assessment of autocorrelation. What we need to understand is the following. And I'm trying to write this one a little bit down. I'm practicing a little bit my drawing skills. So here we have got our timeline. That's our timeline, and we have got different points in time. So that's T. We've got here, 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 and here. So this is T. This is T minus 1, T minus 2, T minus 3, and T minus 4. So now let's get another color. So what we mean by direct and indirect is, of course, T minus 1, that's what we just explored, has got an impact. Of course, this is what we looked at. Also, T minus 2 has got an impact on T. So this is direct impact on T. What we also have, what we have to include, is we also have got that T minus 2 has got an impact on T minus 1, or T minus 3 also has got an impact on T minus 1. So this one here is an indirect effect, and then this one here has got the direct effect on our this is what we're interested in, our T. This is what we trying to establish, is how much does each individual time step has got an impact. So that's a little bit explaining direct and indirect. And one other thing we can do is here we set autocorrelation, but then the next one will be looking at partial autocorrelation. So partial autocorrelation is basically these direct impact. This is, let me just get the right color. This is everyone who has got only an impact on the current one. That's called partial autocorrelation function. And down here with the blue one, that's what we just explored, that basically everything, this one has got an impact on this one here, and so on and so on. This is called our autocorrelation function. That's what we just did. So let's see what we can do by exploring just each individual one, rather than all of these ones together, which we already explored. So for this one, we have got a library as well, and it's called PACF. So this down here is called ACF, and up here, this is called PACF for partial autocorrelation function. All right, let's switch back to our code. And we're gonna be SGT. We're using the same library, plot. And plot, we need to do, hold on, plot underscore, and then it's PACF. So that's partial autocorrelation function. df dot market value. There you go. Market value. The legs we want to explore the same as before is 40, 0 equals, and we said false, correct? Yeah, false. And method. So we have got certain methods available. You can see here what the methods are, I think. At this point in time, I don't want to go through all of the methods, but we're using or less. That's our method we're using. Order of least squares or less. That's the method we're using for our exercises. TLT.title. Now we say PACF, and we have got the FTSE. That's our market value time series. Size equals 24. And PLT, I just did already. Why? Our limit is minus 0.25. You don't need to put this one in there. It just will get a little bit tiny, I guess, when you do that. All right. So now what we're going to look at is the impact. So what we can see here is that only the first leg is significantly larger than 0 compared to the ACF function. So that means that if you're comparing the impact of each individual one to the current date, actually only the one day before that has got a high correlation. Here you have got, a little bit down here, there might or might not be. But by just looking at each individual point, how much effect it has got on the current date, we can see that it's only the date t-1 which has got a big impact on the current date. All of the other ones don't really. And what we have seen up here in comparison, ACF market value, is that all of these effects that they have got actually an impact on today's date just means that they are intercorrelated with each other. So you've got, for example, t-20 has got an effect on t-19, 18, and so on and so on. And just AC basically adds up. So here we can clearly see that when we're talking about partial correlation and we only looking at the impact of each individual time point, we can only see that the first one after our day, today's date has got a big impact. We can have got a quick look as we did in the past. How does it look for the random walk? We do an RM here. We say PSC of random walk. We run the same thing. And as you probably can see as well, is random walk is very, very similar to our market value. All right, so why do we talk about ACF and PACF? That gives us a very, very good indication of when we're doing, let's say we're generating a model and we're talking about the autoregressive model, how many legs do we want to include? So if we just looking at PACF, we might not want to include too many legs for our model because they don't really have got a big correlation towards our current date. So now we're coming to the autoregressive model. It's called AR. So the first part of our ARIMA model is AR. For this purpose, I just have to switch back and I have to just quickly make you understand what I mean by all the coefficients and everything. Let me go back to my drawing. I just spent a new page and make it nice and white. And we start drawing. So here we go. So we say auto regressive model. AR. So the model itself is x of t equals a constant plus, and then we need a coefficient called phi times x t minus 1 plus epsilon of t. That's our autoregressive model. That's what we want to fit our forecasting model. So as I said, values of x on the previous period. So that's x minus 1. We have got a constant c. We have got a coefficient, which is called phi. And then we have got residuals. So residuals are usually these epsilon. So that's residuals. Here we have got our coefficient. And this is our constant. So what we're trying to do with our autoregressive model is we're trying to find the constant and we're trying to find the coefficient. Residuals we can always explore later on what we're going to do. But for the time being, this is the tool what we're going to concentrate on. So one key thing is, as you can see here, this is basically just the model of one leg. So you have got t minus 1. But then, of course, you can extend it to t minus 2, to t minus 3, and so on and so on. So we have to decide how many legs do we want to include. So later on, it will look a little bit more like x of t. For 2 legs, for example, the constant remains the same. We have got phi 1 times x t minus 1 plus, and then we have got a phi 2. So that's our second coefficient, xt minus 2. And we still have got our residuals, which is epsilon of t. So that would be like autoregression model for 2 legs. And this one would be an autoregression model for 1 leg. And we can do as many as we want. So let's start coding that up. So autoregression model, AR. We need 2 more libraries. I can plug them in here. And I give it to you on the chat. And oh, thanks. Someone actually caught my typo. Thanks very much. It's always helpful that you catching my typos, and I know that you're still with me. So let's do autoregression model, our first one, and we just want to have got 1 leg. So we just coming back and we just want to explore what he's saying here is the first one is x of t. We want to have got a constant and we want to have got 1 coefficient. That's all we want. So for starting this one is we call this one model underscore AR. And we say ARIMA. So in the past, just to explain, in the past, there was an ARMA model within Python that got discontinued. So now you only have got these ARIMA model. That confuses everything a little bit because we're starting off with just autoregression, so only the first part. So it has got 3 parts, ARIMA model. It has got autoregression, moving average at the end, and then it has got also a differencing component, which is the I. So for this one, we're just using the ARIMA model, df dot market value. Market value, here we go. And then there's something called order. Order equals 1, 0, 0. So that's important. Is basically what the order means is it's the same as what ARIMA says. So we say the first one is first order of the AR model, autoregression model. The 0 compares to, and we will explore this one later on, is differencing. And the 0 is how many legs we want to include for the moving average. We haven't talked about moving averages yet. So we're just saying AR equals 1, all the rest is 0. All right, so then results, AR equals, so what we need to do is we're building the model with the first one called model AR, and then we say result LR is model underscore AR dot fit, because what we want to do is we want to see how well our model fits. And then we say print results underscore AR dot summary. All right, so just ignore all of these. There's also a model called Sarimax. We're not talking about this one in this lecture. That goes a little bit beyond ARIMA, but we just have got a quick look on our observations, and we see what the observations actually tell us. So as you remember, is we want to look at the constant and our first coefficient. So here we can see the constant. That's our constant. That's a 5090. And then we have got the coefficient called 0.998. So in this case, we have got a very, linear coefficient there. We can see the p-value is 0 in both, on both terms, which basically means that both of them are significant. For the time being, sigma 2, we ignore for the time being. We're just looking at the constant, and we're looking at the first coefficient. So ARL1 is basically our let's go back here. That is our coefficient here, phi. Phi is our coefficient, and here in our list it's called ARL1. Then we can see that both, as I said already, both p-values are going to be 0. And we can have got our log likelihood, and we can compare this one later on with other models. And we have got our fitting criteria, which is the AIC, is this number, and we have got the BIC, which has got a different kind of penalty factor. I think that's log, and this is non-log, to see how well the model performs, considering the complexity. All right, so how do we, now we have got the model, we assessed how good the model is, or we have got our constants, we have got the constant, and we have got our phi. We know how well it fits of our current data set. So now we want to forecast. So we're predicting, let's say we're predicting the next 2 days. So how are we going to do this? We say just print results AR dot forecast, and then we say we want to forecast 1 day, and we take the same thing, and we want to forecast a 2nd day. So that's our predicting the next 2 days. Let's just put it on top. I give you the code later on, so you can see what we actually doing is predicting 1 and 2 days in the future. Okay, we have got a little bit of a error there. Forecast yeah, there's an E missing. I know. Okay, let's see. That works. Here we go. So now we have got our last date in our time series was that date, and now we're predicting the next 2 days. So we have got a very simple model. We explored the coefficients, we fitted the model, and we forecasted the next 2 days. So let's see how our model behaves when we're using more than just, I just give you a quick second. If you can raise your hand that you are right where I am at the moment, so you are able to follow, or if you need any code I need to copy paste into the meeting chat to catch up. Just let me know, type it in the chat or raise your hand if you are there where I am, so we can continue from there. The reason is a little bit is to save a little bit time, I will copy paste now code from up here down there. So you should be able to reach that point what I have at the moment. So anyone? Can anyone raise their hand? So I know that you're still there. Just one. I just need one person raising their hand. Otherwise, I think I'm disconnected from the internet. No one? Yeah, here you go. Thank you. Thanks, Ben. I was just a little bit concerned that maybe I'm on mute and no one can hear me. So thanks very much to confirm that you're still with me. All right. So let's see. Let's look at the same model. But what we want to do now is we just copy pasting it from up here down here. And please don't be shy. Just type things in the chat. You know, it's always a little bit better to type along and experience everything, because I know that usually at the end I will provide the file as I promised, but you will not look at the file maybe for a week and then you don't know what we did in the past. So please type with me, and I think you're getting a much better experience that way. So model AR, and now we're doing a model AR _2. So we want to do a 2-leg, so we want to explore 2 legs. Of course, the only thing, we still need the same data set. We need to change the order from 1 to 2. So now we're doing 2 legs. So going back to our autoregressive model, now we are down here. We need a phi1 and a phi2. We have got a constant and we have got a phi1 and a phi2. The results, of course, they need to fit the model number 2. And here we also AR _2. Of course, we want to have got the results also of 2. All right, so I think I put everything, I changed everything. There's 2 there, 2 there, 2 there, 2 there, and we can run that. So here we can see now is log likelihood is just a quick comparison, 62, 6 to 1. So it came up a little bit, and the AIC 251, that is went up a little bit as well. Let's see. As I said, we have got the constant. The constant is is about the same. So we're expecting the same around the constant, but now about the same. We have got phi1, which is 0.9811, and we have got a phi2, which is 0.017. And there we can see that the p factor is 0 for the constant. For phi1, it's 0. And then for phi2, it's 0.05. So what same for the p factor is, we think that everything is significant which is below 0.05. So in this case, we have got 0.08. So we would not necessarily think that phi2 is a significant factor by predicting our time series. So, comparing the first model with the second model, I would say probably the first model is a better choice, because adding another leg and adding complexity doesn't really improves our forecast. So let's do one more. We can do another one, so we can generate from the From the 2 legs, we can do now 3 legs. So let's see how that works. So we have got ARIMA model 3, order of 3, AR 3. And now we're building up a little bit our own little library with all of the models. We're generating all of the models, see how it fits and get the summary. So here we go. So now we have got 3 phi's. So we can see that the first one is still significant. So we have got a constant. We have got L1, which is our phi 1, is still significant. The second one now becomes significant. So it is below 0.05. And the third one is also significant. So I would say probably third model is probably the best fit. So we can compare. So let's compare the first with the last one. So what we're looking for is we want to have got a higher log likelihood. So let's see. The first one had got log likelihood of 622 for the numbers, and here we have got 615, and since it is negative, it actually has got a higher log likelihood. So that's what we're looking for. That's what we want. We want to have got a lower information criteria. So AIC, let's just pick the AIC. AIC, the first one was 251. And then here we're looking at AIC 241. So that is lower. So it's about by 10 is about lower. So we can say that we would prefer, in this case, we would prefer that this model, which has got 3 legs on the autoregressive model, is a better model for our purposes. So what I want to do is I want to give you a quick tool how we can compare easily the different models. So we want to do that we don't always have to scroll up and down. We would like to have got one tool which can just run, and it gives us a good indication what tool is better. So we can say log likelihood LLR test. And we just have got a very short script. We need one library, and I will copy paste this one into our box there, so you can pick it up from the text. That's the library we want. And we're defining our LLR test. This is what we call it. We need a model 1 and we need a model 2. So, and we need the degrees of freedom, df, and we set it to 1. So that's our default. So this tool you can use in every kind of model comparison. So I would save this one down. I think it's very useful. So we say L1 equals model 1 underscore 1 dot fit. So that's what we did above. And we want to get out the LLF. This is our log likelihood. We do in a model L2 equals mod underscore 2 dot fit. Hold on. Fit, yeah, same thing. LLF, that's our field. And then LR, so the comparison is 2 times, what did I say? 2 times L2 minus L1. And then P, that's our result, equals, and then we need the chi function, chi2, that's what we imported up there, dot SF. And then we just basically put in the LR, we calculate above. We need to include the degrees of freedom. And I can explain to you later on why we need that. And we want to round that number. So say round of the last three decimal points, and we say return is P. That's our little function. If that was a little bit too quick, I just run it quickly, and then if it runs, then I will copy paste it into our chat as well, so you can catch up with that in case you did a typo error. So LLR test, that's our function. And then what we want to do is we want to compare model AR underscore 2. That's what we generated. And always make sure that the less complex model comes first. And then model AR number 3. All right, here you go. We run this one. And there we can see we just did a quick error in there. So I was a little bit too quick with my typos here. Let's see where I've got the problem. Mod 1, mod 2. That's okay. And it says LR. LR, there's a equal sign, of course, missing. Let's see if that was a problem. All right, that works. So here you go. I give you that code. I think it's useful. And what it does, it gives us a very, very low p-value. So it says that basically model 2 is not as good, or model 3 is better than model 2. We can do the same with model 1 and model 2. And we do that. Model AR, we didn't call it 1, we just called it AR. And here you can see it's 0.25, which confirms that the more complex model, model 2, is not better than AR1. So we have got either we pick AR1 or AR, or we pick in AR3. All right, so we did that. What are we going to do next is we just generating another model, and we can use the code from up here. So we want to use a model called model 4. So we're just adding another one to building up a little bit. So we say AR4 is order of 400. So that includes 4 of our legs. We have got a result of, that's number 4. It should fit number 4 in there. We print the results of 4. And now what we can do as well is we can add the function. So the functions we run here, we can say that print at the end, and we can say print LLR test. And this should be plus str, so the string. And then we basically taken the LLR test from up here. So that's LLR underscore test. And we compare model underscore AR underscore 3 with the new generated one, which is model AR underscore 4. So we just put it at the very end. So if you're running the entire thing, what we did in the past, it will also give us the results at the end. So here we have got all our coefficients. We have got phi 1, 2, 3, and 4. We have got our constant. And then at the very end, it tells us LLR test 0.0. So that means our model is considered better than the previous models. We could probably see the indication when we compare the log likelihood we did already. If we're comparing AIC and BIC, that went 217. Let's see, 217, 241. So that definitely went down. So AIC also went down. So we can make sure that, you know, we have got a better prediction on the model number 4 compared to the model number 3. All right, so that's number 4. And let's do one more. Let's do number 5. So we can, hold on, let me just grab this one. grab this one, go down here, and now we're generating model number 5. So number 5, very easy. We just need to change the numbers. We pick it up from up there, and it's model number 5, fit number 5, summary number 5, and now we compare number 4 to number 5. We run that. And here we can see that it leads a little bit. So it's 0.03. So that's getting a little bit close. That's now we have got an LLR test, which is still better than model number 4. But let's see, let's run one more. Let's run number 6. Model number 6. Now we're getting very quick in changing everything. So we're comparing number 5 to number 6. So we're including another leg and see how this goes. So AR4. Oh, I need to copy everything, I guess. I need to still include that one here. Sorry about that. A little bit too quick. We just have to generate first our model before we do anything. So we do a number 6. And here, number 6. Let's see. That runs. And our result is, it gets lower as well. So I think we just have to take another one. Let's see how far. I just did a little bit research. Let's run a couple. So what we can do is we can just pick this one and just run this one down here. We say model 7, we generate, and we number 7, and we just run 2 more without just looking at the results and see. We're just generating them. 8. So we're exploring up to 8 legs. Because what I want to do is I want to show you where actually it's not getting any better. So we're generating number 7, and we're generating number 8. Let's run these ones quickly. All right. We don't look at the results. We just running this one. So we're running 6 to 7. 6 to 7. Let's see what the outcome is there. So it's still better. So 7 is still better than 6. And let's run the last one. Hopefully that works as I did in the past. We're comparing 6 to 7 and 7 to 8 in this case. All right, so now with our model number 8, now we're getting an LLR test of 0.56. So 0.56 basically means that's not really improvement of the model. So in this case, we just have got the AR model available. This way we should stop. So AR model number 7 would be the best one. It doesn't really makes any difference to go any higher. So this is where it's going to stop. Let's see just a quick check of, copy this one down here. We can also, we don't have to do 1 to 2, 2 to 3, 3 to 4. What we can do as well is we can compare the initial model. Is the initial model still worse than number 8 or number 7? Let's see, number 7. And what we need to do in this case is now we have to increase the degrees of freedom of 6 because we're not doing 1, 2. We're just basically jumping from number 1 to number 7. So we need to increase the degrees of freedom by 6. And we run this one. And we will see our model number 7 is a better fit than our initial model with only one leg. So that's what we expected. So one thing is, so that sums up a little bit these AR models. What we have to say that is AR models, they're not really doing very well in non-stationary time series. So when we looked at our market value time series, we know it's non-stationary. It has got a trend. We looked at this one in the past. So our AR model is working well. Our AR model likes to have got a stationary one, which it can predict much better. So let's have got a look what we did in the past. So SDS 80 Fuller, we're doing our 80 Fuller test. This is how we're going to test our stationarity, so market value. And we did this one at the beginning of the course. Here we can see 0.33. That's not an indication of stationarity. What we want to do now is how we're going to get our time series into like a stationary time series. So let me just plug this one. That's a very simple one. We can do is we're going to work with returns. So that's what we're trying to do. So let's draw returns, very simple. That's the calculation we're going to do is we've got the price. So the price, hold on. Am I drawing or not? Hold on. P, the price of the current minus P t minus 1 divided by the P of t minus 1 times 100. So that's our returns. All right, let's see if we're converting our time series in a time series of returns to get a better result on our model. So in this case, what we need to do is we're just using, just general Python commands. Is we've taken our df. We want to include another column called returns. And we say equals df dot market value. There's something called percentage change. So that does it for us. Percentage change. Here we go. Of course, it's only 1 because we say t minus 1, and we multiplying it by 100. That's what we just did. df, of course, equals df dot ilog. And what we need to, of course, get rid of is our very first entry, because the very first entry doesn't really has got any returns. So we're saying that ilog starting with the first until the end. That's it. All right, so now we have got, if we say df, you can see our data. We have got market value. That's our FTSE. That's our white noise. That's our random walk. And now we have got the returns. Here in this column, we have got our returns. So let's see how it looks like now at the Dickey-Fuller test when we're looking at the returns. So sts.adfuller df.returns. So let's see. So now you can see at the second number, this is a very, very small number, e minus 24. That is, a very small number. So that confirms that that out of a sudden we converted our time series, which were the prices, in returns, and now we're dealing with a stationary time series. Let's plot this one. So we did already earlier, we did an assessment of what we think, how many legs do we need. So we can have got log is sgt dot plot. Just trying to make it quick. ACF, and you can copy it from above. df dot returns. Legs, we're looking at 40. 0, as we already figured out, is false. Don't include the first one. plt dot title. We call it ACF assessment from the FTSE returns. All right. And we make it size equals 24. And plt dot y is minus, that's just my scaling, 0.09. I just played a little bit around with it, so you will see it probably going to fit very well. And we run that. Oops, 0.06. There you go. There you can see the scaling difference. All right, so now we can see our returns. So we see in our returns, they are certain legs which are significant and some of them which are not significant. So we can see that in this case, t-1 is not really significant. t-2 is significant, and it's on the minus side. So it is basically impacting our current one in the opposite direction. So sometimes it's when you see in prices development, it's like you've seen a big jump on one day and then it reverses on the next day or the day after. So that's what it represents. So we can see that, you know, the second, the third, the fourth, and the fifth, and the sixth, they probably have got a big impact. The seventh, not that much anymore. We have got a little bit on the eighth, and then we have got a whole bunch of ones which are not really significant. So this gives us a good indication already what we think is significant if we take in the assessment of the ACF. So we remember this includes all of them. And when we're looking at the partial one, so I just copy pasting this one down here, and we replace ACF by PACF, and we need to, of course, include the method. More or less. We say PACF returns and keep the same scaling. I think that might work as well. And we run this. And now we're looking at our returns. And then we see here, it's a little bit clearer, but it is not really different. So that's what, you know, that's what we wanted to see is for stationary events, out of a sudden, the differences between the different time lags, comparing the ones which are, you know, in between and each individual one to the current date is not really that different. So you can see if you're comparing the charts, you can see ACF is very, very similar to PACF, which makes sense because, you know, you don't have got the trend anymore. So you don't have got these interactions within each individual time lag. This is why where they look very, very different. And then from there, we can say that, okay, if we're generating a model, we would probably generate a model 1, 2, 3, 4, 5, 6. Probably 6 would be, using 6 legs would be a good choice. Not going much further because then we have got a whole bunch of legs which don't really have got any significance. All right. So in this case, I just do this one very quickly, and I leave this one a little bit for your homework because I want to get to the next part. But what you would do is you would do model, and then you call it return, for example, return AR underscore 1 equals REMA, same as above, df dot return. It returns. There you go. It returns dot and the order. We will start first, as we did in the past, with a very simple one, 0.0, and results from the returns. AR underscore 1 equals model that's above this one, return AR 1 dot fit. So you've got everything above, nothing has really changed. Results equals returns AR underscore 1 dot summary. And we run that. Let's see if I made any typo error. I did not. Here we have got our results. Log likelihood minus 7,929. Let's see what our last one was here. It has lowered, by a lot. You can see here it's 27,596. Down here we're talking about 79,29. And then AAC has, from the last one, AAC is 55,209, 55,209. And here we have got 15865. So that is much, much lower than above. So we can see that by converting, just for the simple model, comparing it to the most complex model, what we had for just the prices, now we're ending up with a much, much better prediction. So if you want to do this as homework, just use higher legs to see how this is developing. And maybe you can come back to me, and if you run all of this 1, 2, 3, 4, 5, let's say you're running it to 5 legs, you should see that it's not really improving after 5. And what the comparison is with the most complex one when we just looked at the prices. So I leave this one a little bit with you, but now you can see that if we're talking about stationary time series, this model works really well. If you're looking at non-stationary time series, it doesn't really work that well. And that brings us to, let's see what the next one is. That one brings us to the next chapter. So we have got 80 for returns. That's what we did. Just trying to comparison of different ones. We can normalize. I don't think we don't need to normalize this one at the moment. What we want to do is now is we want to see about the residuals. So you remember in the past, I talked about residuals, and we can generate these residuals. Let's see. Just want to see. Let's returns. We have got our time series here, so we can use the non-stationary one to see what our residuals are. And we can also use a model for this one. Let's do the following. Let's do a following. We can say df residuals price. So everything which is the residuals, which was our epsilon, equals result AR model 7, and then we can say residuals. All right, so that's from our AR model. number 7, that generates our residuals. All right, that's how it works. Let's see, takes a little while. I think I'm a little bit stuck here, but it generates them. Let's see, df. When it generates that, here you go. So we have got the residuals and price. So what you can do as well is here is you can actually look at the residual ones, how they behave with our Dickey Fuller test, AD Fuller test, df dot residual underscore price, and we can see how they're distributed. So they're distributed as a stationary one. So that's a stationary time series, the residuals, and we could run the same modeling what we did in the past with the residuals, and just give you a little bit of a view how it looks like. I'm just copy pasting, and you will get the code as well. I promised. Give you a little bit the residuals of the price. So that looks like a very stationary time series. You can see here 2008, 2009. You have got the big residuals there. So later on, when you're looking at the volatility, you can explore this one a little bit. What I want to do is, I've got 5 minutes, so I'm trying to speed it up a little bit. We want to look at the moving average model. So let's see. Moving average model, that's our second part. So let's just do that one very quickly. It's the same as what we've done already. So from a model perspective, we can basically come up with a formula. So the formula will be R of t. Let's see. Hold on. R of t at the time t is a constant plus, and then we have got theta. So we take in another coefficient theta 1 epsilon t minus 1 times epsilon t minus 1 plus epsilon of t. So, and this is called the moving average model. So now what we need to do is we also have to generate these coefficients. So the value R of t is the current. That's the current. The current period. We have got the coefficient here. That's a coefficient for our moving average model, efficient model. And then we have got the residuals. Residuals of t minus 1. And here we have got the residuals of t. So what it does is we have got these two residuals, and that's why I showed you earlier is how you can explore the residuals. One important thing I want to mention is how do I determine, just looking for our assessment, how many legs should I include? And a good guidance is, if you're looking at AR models, you will use the PACF analysis. That's what we did. If you're looking at our moving average, our new one, that's the formula above, moving average, we would use only the ACF. So if you want to decide how many legs you want to include for the AR part of your RMM model, let's say it's our RMM model, using the PACF as analysis of how many legs you want to include. And we did it a little bit manually in the past when we run through all of them. And for the MA model, we do the ACF. So since I have got maybe 2 more minutes left, I just will use a very, very simple MA model. And the very simple MA model will be the following. I don't type it, I just put it in here and you can download it. It's not very much different. We take returns as well. So let's take the returns. MA model, so moving average. ARIMA stays the same, but what you can see here is in the order, now it has got AR is 0, differencing is 0, and then for moving average is 1. And then we do exactly the same as we did before. So there's nothing really different. And then here we can see our results of the moving average model. So that gives you a little bit of moving average model. And to wrap up, what you can do as well is you can do an ARIMA model. So that's our MA model. And our ARIMA model will be just do the returns, ARIMA model. And then we literally just, the only thing we change here, I just have to change a little bit the turns order, is one for AR and one for MA. And the differences in between, you can play a little bit around with it, but it's not really that significant because we're talking about returns, which are anyway stationary. If you don't have got a stationary time series, what you would do is then you would actually put this one to maybe 1 to be able to convert out your time series from a stationary one in a non-stationary one. So let's do this one very quick. We run this one as well, just for completeness purposes. There you go. Do this one here, do this one here, do this one here. And let's see if that runs. Here we go. And here we go, you're getting the results here. So you can compare a little bit of log likelihood. You can use the AIC for comparison. You can also use the log likelihood test, which we generated. So let me just give this file a name. Give this file a name of coding for risk management, October 6th. And before I issue that file, Ben, maybe you can help me to start the survey. And
Absolutely.
If you can go very quickly to the surveys, just 3 questions, but we want to get a little bit your input on if that course is useful, if you learned something, if you would consider to take the full course, if it's available. So please enter these questions. And at the same time, I will download the files. So you have this one as your reference. I will download 2 files, one as a Jupyter file, one as a Python file, and we'll post them on the chat. So please take the survey, and as a reward, you will get the files.
So just to confirm, thank you, Marcus. There's a SurveyMonkey link in the chat. If you click on that link, it'll take you to only 3 questions. And the 3 questions are basically asking, this workshop is obviously a voluntary workshop. It's not for credit as part of the MSc program. And the questions are basically asking, would you be interested in taking a course, and what your aspirations are for Python? So if you look in the chat, there's a survey link. Please go there and fill in the 3 questions. Thank you.
Thanks very much, Ben. So since you are busy with that, I just downloaded the 2 files. Hopefully they're coming up. Here we go. And then I will post them on the chat so you can download them from there. And you can, oh, sorry, I just sent it to Ben. Sorry about that. To everyone, of course, I need to send them. Here we go. And what I would encourage you is play around with the file. It's like I did a lot of, at the beginning, we did, all of the legs. Then I had to speed up a little bit because, 1.5 hours are not really enough time to go through everything in detail. But what I want you to do is a little bit explore the time series, see what is a good model to fit, and just come up and confirm it with the analysis you did in the past. So, just choosing how many legs you want to predict your time series. So I hope that was useful. I know it was a little bit fast today, but hopefully it was a lot of repetition because I copy paste a lot of things, and you do have got the files available. If you have got any questions, let me know. If you find anything out, if you have got any suggestions, please come back to me. This, I think, second or the third time I'm doing this, but I'm always open for if someone has got any suggestions how to make it more compact. I know there's a lot of things we haven't talked about it. So if you have got any ideas how to shorten that that presentation, then that's also appreciated. So thanks very much for joining. Thanks very much for taking the survey. And I hope I'm going to see you. I think there's another course next week. And then the following one will be Monte Carlo simulation. First time I'm doing Monte Carlo simulation on Python. I'm very excited about this one. And I hope I'm going to see all of you in my colleague. I think Ben, he might do one next week, but then it's me again in 2 weeks time. So thanks very
Can you
much.
share your email in the chat box, please?
Absolutely.
Thank
I
you.
will put my email. I will put my let me just copy paste it over.
I will just do one
Here you go.
more advance for the survey. We've got 5 responses. There's 8 students. It would be amazing to
let's
get
go.
all 8 people responding. It's only 3
Let's go.
questions. It takes 20 seconds. Here's the survey in the chat box again.
Thanks very much, Ben. By the way, Ben, you doing next week?
I'm not next week. I think I'm
What a mess. Okay, I'll try that again. Okay, well, let's jump in. So there is the link. I hope everybody is able to see it. And with that link, I will share my screen and show you that version of the link myself. So I've now shared the screen, and let me come over here to a fresh window. Okay, so hopefully I am now successfully sharing the link, and you're able to see my screen. Can someone just chat an okay, just to let me know that you're with me? You've got the workbook, and you're able to see my screen, or just call out. Just let me know that things are going okay. Any confirmations out there? I just want to be sure that you're all able to hear. You've got the shared screen, and you've got the link, and you're ready to go. Can I get a confirmation when you're ready after you've clicked the button to what to the after you click the link to the Colab notebook?
Yes, sir.
Yeah.
Okay,
I'm
thank you.
ready.
Excellent. All right, then let's jump in. So this topic will be building a lending business. And what is so useful about simulating the data is it lets you learn all the interpretations about a data set. When you arrive at a company, they are going to have massive amounts of data, and each individual column is going to be a concept, and it's just going to have a label. It's just going to have a column name. And you have to get from that label to an understanding of what that data represents. So for example, probability of default. Well, what is default? Is it that the loan ever defaults? Sometimes default just means to fall behind in a payment. So, for example, when nations default on bonds, we say Russia defaulted in the ruble. That was something that happened in 1998. It was a very big deal. But that didn't mean that they never paid anything. That just meant that they have now missed one of the coupon payments. And now the value of the bond is going to fall because people are afraid that they will miss more payments. So sometimes to be in default just means to fall behind. It doesn't mean to never pay anything. So all these subtleties emerge. And when you simulate the data, it's your opportunity to build a little universe and decide what all the different names can mean. And that way, once you arrive at another company, in your mind, you have an inventory of all the possible different interpretations. And then you can ask good questions and say, all right, I see this column is called probability default. What do you mean by that? Do you mean being late, or do you mean written off? You don't expect any payments anymore and you've sold it? And in fact, yes, so there's three categories: being late, never paying anything, and never having paid, and you're also going to resell it so you no longer own the loan. There's all sorts of levels of interpretation. Okay, so, but I want to do what I promised. I want to get our hands onto the code. So I will start us coding, and then I'll ramble more as we code together. So here is a collection of videos that talk about the various risk metrics that you can do once you have the data simulated. And right now we're just simulating the data. This is also great because once you really build the data set, you will have such a rich understanding of it that you're ready to analyze it. You will know what every field is because you made it. Okay, so let's start off. One last little detail before totally jumping in. This workbook, I can click over here to the table of contents, and this workbook is organized into this workbook is organized into lessons. You see lesson 1 to lesson 12. This content appears in our applied coding for risk management class, and that's something that we do. And what's great about that class is that these ideas are taught one little step every week. So you take one lesson, lesson 1, lesson 2, lesson 3. Each happens along the week. You have time to think about it. You have time to live with it. And then if you're taking that class, then you can also, of course, come to these seminars, and then you get another point of view. You get what it's like to do it longitudinally, the whole thing all in one day. So for students that take the class, you get the double experience of living with the ideas stretched out over time, and then also doing the whole thing all at once. And of course, you get 2 opportunities to learn the concept. Okay, and so lesson 1, we are going to simulate dates for our loans. And I am going to simply start running it, although it won't work on my computer at the moment because I have this in incognito. And so when I hit Shift Return, it's going to say, hey, you've got to sign in so Google knows who's using their processing. No, that's not a problem. I will highlight this link and I will come back to my Columbia login. I made my browser Columbia blue, so I know that it's Columbia when I log into my Columbia Google account. I'll come over here to a fresh link, to a fresh tab, and hit enter. And now I have my notebook. All right. I'll reveal the little table of contents, and I'll click L1 just to scoot down a little bit. And here we are. I'm going to import NumPy. I'm going to import matplotlib, and I will import from date utilities relative delta. Relative delta lets you look at relative times. So that means I could have a date and I could add 1 to it, and that gets me tomorrow. And if I add 10 to it, I'll get 10 days in the future. So I could add and subtract time increments. I could also identify increments and add. So I could add 1 month, I could add 1 week, I could add 1 year. Okay, so let me run that. And it's going to tell me that I'm not the author of this. I've got it from somewhere else, but that's okay. So you're getting it from me. I promise I didn't put any bad things that are bad for your computer in here. And let's keep on inching along. So now we're going to have an origination date. Actually, I'm sorry. Give me one moment for one more thing. I'm going to record this so I could use it to develop this material. But I'm not allowed to, but that's going to be for private use. But I will try to add videos to each of these sections on my own, so you always have access to video training, but I can't share the videos. Okay, so we have our sorry, one moment.
Recording in progress.
Okay, so we have our origination date. The origination date is the date upon a loan was born. So like superhero origin stories, that's when the loan was brought into being. And if you're a salesperson, your goal is to originate loans. If you're a salesperson for a lending company, your goal is to bring them to life. You originate those loans. The origination date is now the date that the loan was born. And we can see that we have a origination year of 2020 and a month 12. So this is December of 2020. And we can take the date time. We could simulate the year, simulate the month, and have this be the first. So this is having this is going to be for 2020 on month 12 and day number 1, and I have date there. And at the end, I just type data reg so we can see it. Don't worry, things will get much more complicated than this. I just want to I'm just warming myself up and warming you up as well. So there is our origination date. And we now have a simulated date. So this could be for like one loan born on 2020, December 1st. Now let's do a little bit more. Let's have a start year and an end year, and let's simulate. So we're going to use NumPy. We're going to simulate we're using the random object, the random module. We can use random interval and select random integer and select between the start year and the end year. And we could simulate a month. And the month is going to be from 1 to 12. And then we'll take that, then we'll do the same code that we had before. So the very same code that we had before, except this time the year and the month are stochastic. Stochastic is the fancy way of saying random when you're in the context of time. Okay, so we just simulated April of 2019. Let's do a couple of more. April of 2014 and July of 2011. Okay, so now our homework is to simulate 1,000 origination dates. Okay, let's come in and add a little code snippet, and now we have to simulate 1,000 of these. Okay, that shouldn't be too hard. And as I stated, I'm stepping in, so I'm actually a little bit cold, which is good because now we can all really do it together. Usually, of course, I would warm up before presenting, but since I'm cold, that makes us all kind of like we're all peers. We're all doing this together like it's all of our homework. So let's see. If I'm going to simulate 1,000 dates, one thing, I know I could do this with a loop, and maybe I will start with a loop just to be sure I can actually do it. And then I will see if there's a vectorized, more efficient way to get this done. So let's start just being sure that we can get it done. I will have for I in range 1,000. And I will, actually, I'll steal this material. And I will highlight it all, and I'll hit Shift Tab to move it all back so it's together, and then I'll hit Tab to move it all to be in the same place. In fact, I'll hit Tab twice. I think 2 tabs is the usual way to go. So I mean 4 spaces. I think 4 spaces is the Python standard, and each tab apparently is giving me 2 spaces. We can see that from those little dots. If you look closely on the screen, I've got 2 little dots. Okay. So there, and before this, I will make a list. So I'll call it list of orig dates. Okay, list of orig dates is equal to a list. And then I will have list of orig dates dot append, and I'm going to append the simulated date. Okay, I will run that. Great. And then I will, I don't want to print out all 1,000 of them. Let me see if I get some properties of it. Maybe I could have my list of orig dates, and then I'll look at the length of it. Okay, I've got 1,000, and I'll also look at the first 5 of them. Okay, so there we are. We have 1,000 dates simulated. So if this is all easy for you, easy peasy, that's good. Go ahead and take a moment and see if you could do a more efficient coding of this. You could either do your efficiency in terms of Python using a list comprehension, or you could also try to be efficient in terms of using NumPy to get a vectorized collection of dates. And yes, go ahead and start working on that without me if you know, so that you're ready to go. And in the meanwhile, does anybody have any questions? Are we all in sync as we begin together? So I'd like to emphasize, and I'm just rambling. If you're already typing, go ahead and keep typing and keep working and ignore me. But for everybody else, if you have questions, if you want to chat me your code, if you're stuck, or if you just want to catch up, this really works best when you're actively typing, and it also works best with double monitors. So if you have a single monitor, like you kind of have to squish everything onto your screen. Any questions out there? Okay, if there are no questions, then I will then try and do this again with a list comprehension. So first, I'll just warm myself up. I will have print I for I in range 5. Okay, I was just warming myself up to the list comprehension syntax. So there we are. These run a little faster. Python is just built to understand that this can be a way to build a list. And then what you do is you save your list as the result. So in my case, I could have my list of origination dates is equal to that. And now my origination date. So now what I have to do is I have to strategize about this whole thing. So the for I in range 1000, and then I just need to take the engine. The engine was over here. So date time and then I have to take these and I have to actually substitute in the random number generation. So this is efficient in terms of its processing, but it's harder on the brain. And sometimes, you know, your well-being as an analyst is important too. And if you need things to really run fast, you would get some sort of a different style of programmer to rebuild everything in C++. This is conceptual coding. So you want your mind to be nice and clear, but it's not so bad to make this a little bit more efficient. Now I'm just stealing the origination month part, and I'm putting that over here. And I think I got it. And I will be sure after I hit enter. Okay. And now let's take a look again at our results. Great. Okay. So I now have done a list comprehension. I'm more Pythonic. My code runs a little faster, and I'm ready. I'm more quickly able to get the work done. Questions before moving on to the next little mini lesson for us? Okay, then let's go on to our next mini lesson. We're going to simulate terms and rates. So remember that our topic is loans, and we've just simulated the origination dates. And now we're going to simulate how long the loans are, that is the term of the loan, and the interest rate that occurs when the loan is originated. And this is good. So hopefully I'm also warming you up to the terminology, right? So you have a rate that is set at the origination of the loan, and that rate is based on the probability of default that is assessed during the underwriting. Okay, so we have a term, and then it's going to be a random choice between 6, 8, and 12. So we are going to be a small, medium SMB lending. We're lending to small, medium-sized businesses, and we are going to have loans of different lengths, of different terms. And for those different terms, we're going to have different size loans. We'll have 10,000, 50,000, and 100,000. So these are smaller size loans. And in fact, these are very small loans in the scheme of institutional lending. We're going to simulate a random rate between 5% and 40%. I guess at the moment we have a fixed rate, so we need to fix that up. And we have a probability of default of 50%. And we're going to set that equal to the square root of the rate. So what's happening is it makes sense that there should be a relationship between how much you charge and the probability of default. And a nice way to quickly simulate, this is a very, very quick and clumsy approximation, but our goal is to get reasonable data to really feel a universe and learn from that. It doesn't have to be perfect. We just have to get an overview of the universe and what it's like to have our machinery run on the universe. And then you're ready to go to a company and work with their real data, having understood the universe and having understood how to work the machinery. Okay, so we want to have our probability of default be a function of the rate. And one way to do that is to take the square root of the rate. That makes the probability of default much higher. So if your rate is 25%, that is 1/4, then the square root of 25% is 1/2. So you have a 50% probability of default corresponding to a 25% interest rate. I may have said that backwards. I'm sorry. Sorry, I'm taking a moment to think about that. Let's start coding, and we'll see. You can make arguments both ways, but we want the rate to be much higher. So the probability default as the square root of the rate has the it has the probability default growing sort of faster, and it might be better to, probably better have it the other way around, but either one, we'll build our universe and we'll see how our universe operates. So I'm going to take this rate and I'm going to have np.random dot uniform. All right, so we now have a uniform random draw, and the IntelliSense has come up, and it gets me my range. I will have low equal to 0.5, and I will have high equal to 0.4. That was 5%, my mistake, 0.05. Okay, so now I have a rate. And so what I want is I want my probability of default to be the rate squared. I have this backward. So not square root, but square of the rate. Because if I have a 25% probability of default, then I want my my interest rate to be 50%. Yes. So if my interest rate was 50%, I want the probability of default to be lower. You always want the probability of default to be lower than the rate, because the rate is compensating you for the probability of default. Okay, so I'm sorry I got clumsy here. Let me fix this for us quickly, and then we'll go on to coding. If 10% of your loans are defaulting, if there's a 10% probability of default, then you can break even. If imagine you made the very same loan that has a 10% probability of default, if you just charge an extra 10%, and if you can make the same loan over and over again to the exact same type of person, as though you can make duplicate copies, your higher rate is paying you for that default rate. So your interest rate should always be higher than your default rate, and probably non-linearly higher. It should be growing even more so, which is why it's so nice to use the square. And so I'm going to set that up here. And let's now have PD is equal to NP dot, well, actually, I'll just have my sim rate raised to the second power squared. Okay, so there we are. We've got it after a little bit of a clumsiness. I apologize for the mess there. Okay, but now let's go on to homework 2. Simulate and populate a data frame. simulate terms, size, rate, and the probability of default at origination. And then make 1,000 of them. Okay. So we have a data frame. And now we're going to do all of this 1,000 times. Okay. So that's going to take a little bit of work. Let's steal the previous work. So we have the origination dates. All right, so we're stealing that one, and we're coming back down, and we'll come up above, and we'll paste that. Okay, so we have to simulate terms, size, rate, and the probably default at origination. Oh, and it didn't want the origination date. Okay, so I don't necessarily have to have that here, although it makes sense to toss it in. Let's see. Let's grab some terms. So there is our term, and we want 1,000 of them. So I'll come down over here. I'll make another bit. And instead of calling it sim term, I'm going to call sim terms. And then I think I can have as another argument to my NP random choice, I can ask how many. So I have integer and then size. There we are. So my size is equal to 1,000. Okay, let's check that out and make sure that that was right. And if that's right, it should be easy to simulate more of the loan terms. Okay, great. Kind of weird that they're all the same. Let's look at the 10 of them just to. Okay, it seems to favor 12 just randomly, but that's okay. Let's now get our size. So I'll come back over here. Here is size. That should be nice and easy. So I'll have sim sizes. I'll make that plural. And then I will add size is equal to 1,000. And rather than typing it, I'm stealing it. I'm stealing my previous typing from above. I'm coming over here, going to hit delete. I'm typing again. All right. And now I've got 1,000 sizes. Okay. So far, so good. Let's keep on going. The rates. I think this could just be nice and easy. We have our, I'll just try the same trick. Oh, wait, whoops. That I need to grab the size again, copy, paste, put a little space there to make it all pretty and aligned. I'll give that a run. Okay, we've got our rates. Keep on going. And finally, our PD. So sim PD, although the name was changed, it was PD at a ridge. The reason that, sorry, I accidentally clicked into a cell. Let me make everything look good again. Okay, so we have PD a ridge. And when I first did it, I called it sim PD. The reason that we have to use PD underscore ridge is because we have a probability of default that is occurring when the loan was born. But now imagine that the borrower stops making payments. Well, the first time the borrower misses a payment, maybe it was a tough month. Maybe there was just some confusion, some technical error. That's fine. But let's say that the borrower misses a second month. Now you're really worried that they aren't going to pay you. And let's say they miss a third month. Now it's very likely that they're just plain giving up on paying you back. So the probability of default changes with customer behavior. So your original probability of default is just the probability of default that you had at the origination of the loan. So we need to clarify that this is just the probability of default at origination. I'm sorry, every time I double click on this, it takes me into the display. And since this is a NumPy array, I think it will be vectorized. And so I think I will be able to simply square it in order to get the result. Let's see if we have that. Awesome. Yes. So we do have that. And now we have to put that all into a data frame. And embarrassingly, I don't perfectly remember how to do that. I think I can do that by zipping everything up. So I will try to do this by zipping everything up. Oh, yes, you could either zip everything or make a dictionary. And I will try the zipping approach. So let's see. I will have my data frame is equal to pd.data frame. That's all right there. And now, okay, let's see. I will try zip. And I'm going to put all these in there. Sim terms, sizes, rate, and probability of default. Okay, let's run that. Uh-oh, all right, tough times. What did I do? PD is not defined. Oh, okay, well, PD is for pandas. So before I actually get that running, I of course have to import the pandas module. So import pandas as PD. That's not too bad. There's an easy fix there. And let's give that a go again. Okay. And now let's take a look. df.head. Okay, so we're almost there, but what we need is column names. And so I think I can have columns equal to the names, which are term and size and rate and did I double something? Term, size, rate, and PD orig. Okay, that was supposed to be PD orig. Sorry, my mistake. So the probability of default is the rate squared. So and this so if the interest rate is 50%, the probability default is 25%. And that feels good. That feels good. Okay, so then I'm going to change this to PD origination. So I'm fixing my little mistake there. And then my I'll have PD underscore orig. And it's not pretty. Like I want to just put PD there to make it all nice and clean names and have a nice aesthetic symmetry. But I have to specify that the PD is as at origination. It's just so much more helpful. So I have to do it. Okay, let's now take a look again. And okay, there we are. And we could see now the reasonable relationship. So if you have a 27% interest rate, there's a 7% chance of default. If you have a 17% interest rate, there's a 3% chance of default. If there's a 20% chance, there's a 4% chance of default. That feels reasonable. So the rates and the originations, they have some kind of a reasonable relationship to each other. Okay, any questions out there at this point? Let me give everybody a minute to just catch up. I want everyone to have the opportunity to code this, and I'll also take 1 minute for myself just to give myself a cup of water. I'll be right back. Okay, I'm back. I hope you're all able to code along. And let's jump in. So, question 3. We are simulating default. So we can simulate whether a loan defaults. We will have true or false. Okay, and we could put our work there. And that's not too bad. Basically, we're going to simulate a 0 or 1, and then we could have that be truthy. I think that's the way you say it. It's funny. Sometimes you don't know whether something is a joke or whether it's the actual thing. But you can simulate the default. I'm sorry. You could simulate something to be 0 or 1, and the 1 represents true, and the 0 represents false, and that's all good. And officially, it's called truthy when you do that. Okay, so I will just simulate 0s and 1s, and that's not difficult to do. I'm having a momentary blank. Somebody can call it out. Yeah, we can make it a team thing. The answer is sort of coming to me, but if anybody else knows, what's a good way to simulate 0 and 1? Use np.random.integer. And then 0, 1. Uh-oh. I don't think it was, maybe it's just int. Nope. Nope, has no random. np.random. Well, I'm going to go back up and sneak to my, I could make random choice and choose between 0 and 1, and actually choose between 0 and between true and false. But how do I get a, oh, maybe it's uniform with the values set to being discrete. Let's try that. Just a good exploration for us. So uniform. And now my range is from 0 to 1. Okay, so I was able to, so I have low equal to 0, high equal to 1. Okay, so now we have a uniform draw, but what I want is I want to have this draw be of integers. And so, yes, so I have float. And I'm wondering if I set float equal to false. So float equal to false. Nope, it doesn't like it. Okay, so having failed to recall how I could actually simulate in a number range, I will just choose between them. So I could have MP random choice, and then I will choose between, actually, I can choose between true and false. True, false. Aha. Okay, so there's an approach. Okay, we will go with that one. And we've now simulated whether or not a loan defaults. So far, so good. And we could simulate when a loan defaults. Okay, so we're building this universe. We know what it's like to make loans. We've done that. We've made the term, the probability of default, the rate, the date of origination. But now when? So if I have a 6-month loan, does it default in month 4, month 3, month 2, month 6? And that's a concern. So what we can do, we need to build some infrastructure. We need a default curve to tell us when the default happens. And we could have the probabilities sum to 1 so that the universe makes sense. So we now have, and that would be the probability sum to 1, but that doesn't mean that you absolutely do default, right? If the probability of defaults sum to 1, that you might think for a moment, wait a minute, does that mean that that we definitely default? And it would if we don't clarify that this is the conditional probability of default. So conditioned on defaulting, this is the probability distribution of when the default happens. So we have a default curve, and so we have 1, 2, 3, 2, 1, 1, and that does sum to 1. I know that because 1, 2, 3, 4 sums to 1, and we kind of have that. We have 1, 2, 3, and then the 2, 1, 1 is 4. So 1 plus 2 plus 3 plus 4 happens to sum to 1. Well, I mean, it sums to 10, but we have little 0.1s everywhere. So, well, the point is all of these sum to 1. And these are our probability curves. And we also have the default range. So if you're a 3-month loan, you have months 1, 2, 3. If you're a 6-month loan, you have 1, 2, 3, 4, 5, 6. This is just a boring little bit of infrastructure that we're going to need in order to simulate when you default. Okay, so let's run that to make those little bits of ingredients come to life. And now we have SimTerm, and I ran it by accident, but there's not much happening. We have to actually simulate when the default occurs. So we're going to use random choice. So we will have, I'll pick from above, and we will have np dot random dot choice. And now we can pick from different possibilities with different probabilities. So let me demonstrate that right now. So I could have my possibilities be A, B, and C. And then there we are. And then what I need is the probability. And there it is, P. So P is the probability. So I could have P is equal to 0.8.1.1. So I now have these events, A, B, and C, and they happen with probability 0.8, 0.1, 0.1. And so if I simulate this, I should get A a lot of the times. Oh, good, there's a B, but mostly, and there's a C, and there's another C, a surprisingly high rate. Okay, good. I'm expecting mostly A's. Okay, but I realized instead of doing this over and over again, let's be a little bit more efficient about it. And then I'll have my size equal 100. There we are. Okay. And yes, as we look at this, we clearly see that there are lots of A's everywhere. And just to be totally sure of this, I'll make it 0.9 and have this be 0.05 and 0.5. Okay, and now we should just see A's totally dominating. There we are. Good. A's everywhere. So we have this working. And now you could sort of imagine that I put this default range, I put this boring 1, 2, 3 here. That's just giving us the selection. So I could then use this probability default curve in order to return the time that the default happened. Okay, so let's come back over here. Let's have our SimTerm equal 3. Okay, so we're simulating a 3-month loan. And what we're going to do is we can use the term in order to retrieve the appropriate curve. So yes, it's getting a little tricky. It's just getting a little tricky. So what happens is the 6-month range obviously corresponds to the 6-month default curve. And the 12-month default curve corresponds to the 12-month range. And so we need to have these two matching. So let me take this code again, and I'll do it again for us, but this time I'm going to substitute in the default curve. So I'll come back over here. I'm going to paste this. And now let's change things a little bit. Let's have the 6-month default range. There we are. Here is my 6-month default range. Great. Okay, and now let's take the 6-month default probabilities. And I could put those over here. Awesome. Okay, so there it is. So you see it working, but now we have to continue. We have to get one notch fancier. So let's again move things down a little bit. Paste again. Oops, no, I'm gonna grab this and I'm going to make it fancier. So rather than just hard code it and put that number 1 to 6 over there, I'm going to say its default range for sim term 6. And this is going to be my default PD curve over here. And it's going to be for term 6. Let's give that a run. Okay. Okay, we're still doing well. One last time, let's copy this again, put some code above, and let's make this really nice. Instead of getting us stuck with this hard code as a 6, let's put the simulated term. The term could be a 6 or 8 or a 12. Of course, they have to match. It looks like I can only use 6 or 12 because there has to be a 6 or 12 here and a 6 or 12 there. That's okay. So I'm going to take the 6 and I'm going to replace it with sim term. And sim term, I'll make some code above, and I'll have sim term equal to 6. And there we are. But now I will also try the number 12. Okay, great. So we now can simulate when a loan defaults, given that it has defaulted. Any questions at this point? Okay. Let me come on down a little bit and find out where we were. So there's our sim curve, there's our PD curve, and finally sim default time. So we had to actually simulate a default time, and our work goes there. And our homework is to simulate when 1 million loans default and display a table. Observe that the display matches the PD curve. Okay. Okay, we've got a big question there. So let's take this step by step. First, let's get this to work. Let's get our default time. So NP random choice. That was going to pick from 6 and 12. Okay. So we have 2 types of loan. We have 6-month loan and we have 12-month loans. And we now have sim default time. And we've already done this. We already have the answer. Let me just steal it again. There's our answer for doing that 100 times. And this time, in fact, I'll put these two together. I'm putting these two together just to show that now we have a really complete simulation. Now we're simulating when the term of the loan and when the loan defaults. We're simulating those together. So this was a 12-month version. That's a 12-month version. another 12-month version. I'm looking to see if I get a 6-month version where I don't see any loans that defaulted after time 6. Oh, I know what's happening. I'm sim. Okay, sim term. Sorry, my mistake. I had a mistake going. There we are. So clearly this is a short loan. And I'll run this again. Another short-term loan, and now long-term loan. Okay, so now homework question 3.3. Simulate when 1 million loans default and display a table. Observe that the display matches the PD curve. So now what we want to do is we want to check, we want to see that we are actually accomplishing getting this default curve. So for a 6-month, we should have a lot of them occurring in the middle, and the same for the 12-month. And we need to simulate a lot of these in order to get a histogram and see that we really are creating what we think we're creating. Okay, so simulate default times, 1 million of them. All right, we know how to do that. So I'll come over here and I'm pasting our work with 1 million. It's kind of scary, but the computer can do that. Oh, wait, but I have to, do I have 1, 2, 3? Yes, that is 1 million. Okay, so I'll run that. Wow, it's amazing how powerful computers are. So there we go. So I got 1 million of those. And now let's see. We are, what is this code doing? We're importing matplotlib and we're grabbing a counter. And so we're now counting the default times to make the frequencies, and then we're simply making a plot of it. That's great. That's very nice. So this counter module that has been imported, it seems to do all the work. It simply is creating a frequency distribution of this data column, and that's nice. And it'll be easier to just show what that is. So there we are. There's our frequency distribution of this column of data, right? All that we did is we simulated the default times. That was one column of data. It had different things in it. Those things became keys, and the count of them became values. We put the keys and values into X and Y, and then we make a bar chart to show the result. And everything was happening from counter. So counter was the module. We applied it to our data column. It gave us a result called frequency. Frequency gave us keys and values. Keys were the kinds of things that happened, and values was the count of the things that happened. And finally, here we are. And here is a nice distribution. And it looks like it exactly matches. It looks like a normal distribution, but that's not what happens. That's just because it's so symmetric. But if you look back, we had 0.1. Oh wait, is this yes, so for 12 we have, sorry, I got lost. There we are. We have 0.1, 0.1, 4, 8, 16. So it's like doubling 4, 8, 16, and then 20, 20 at the top, and then coming back in the same pattern. And here we are, 0.1, 0.1, 4, 8, 16, 20, 20, and then coming back in the same pattern. Great. All right. So now we can continue working downward. Question 4, simulate history. So we are now going to create histories for our loans. And this is a little tricky. Every loan needs to have existed over time, right? A 6-month loan, if it was paid down over 6 months, has a 6-month history. And we are now going to create those histories. So here's the history of a loan that doesn't default. It has every month, it has a status, whether it's been successfully paid or not. It has an unpaid principal balance. that is how much there is left to pay. It has a probability of default for that month, and that is according to a model. Our model is going to look at, say, and see, have they continued to pay? Have they missed a payment? Do they listen to sales? Do they listen to calls if people call and say, why are you late with your payment? And we can have the amount of delinquency. So if they are delinquent, are they 1 month delinquent, 2 month delinquent, and so on? So we can have histories. And even more than that, we can store the histories with lists. So now we have lists storing the histories. Okay, so, and the reason we're using lists is because the key for those histories is going to be dates. So we're going to have all this information indexed by date, which makes sense. It's happening over time. We have to make this real. And we're simulating data. We're simulating a universe that existed in time. And so every month, whether the payment was made or not, is a date in time. So it makes sense that our index should be dates. Okay, so I will run that. And now let's take a look. We're going to set initial values. The unpaid principal balance, that is the fraction of the principal that is unpaid. And at the very beginning, it's 100%. So we have the number 1 for 100%. The status is active. Nothing has gone wrong yet. The loan is just originated. And we have the probability of default from the model. And at the very beginning, the probability of default of the model is the original underwriting model. So the model PD is the origination PD. And this shouldn't say sim PD. This should say PD underscore orig. Use the origination probability of default. And our delinquency at the date is 0. So we are 0 months delinquent. Notice how these are all dictionaries. And the dictionaries are all indexed by date. And we are free to just immediately refer to them. And we're asking a lot from Python. So the Python language, we're having that language do some work for us. We haven't pre-allocated any memory. We haven't said, hey, we want you to index by date. We just said, you're a dictionary and we're going to give you a key and you fill that key and match it with a value. So we ask a lot from Python and Python delivers to us. And let's see if this works. Great. And let me just take a peek at PD orig and make sure that it's not okay, that's why. I'm going to move PD back to sim PD. And then let's run that again. Yeah. Okay, so one thing we have to do, let's just make up a temporary probability of default. So we could have 0.25. There we are. So just a temporary value. And I'll delete that. Okay. So we have but this should be the PD at origination. And I'm just using 0.25 as a placeholder. Okay, so now we are not defaulted. So we have a loan that's not defaulted. And if we have not defaulted, then we're going to go through the terms. So if we have a 6-month loan, we're going to do loan a month 1, month 2, month 3, month 4, month 5, month 6. And the date of each time period is going to be the original date plus 1 month. Remember at the very beginning when I described relative delta to you? Relative delta lets us increment dates relatively. So we're taking the origination date and we are making a relative change to it of 1 month. And I is equal to 1. And as we loop from I equal 1 to the number of simulation terms, we get to increment the date. Then we use the date to populate the these values, the unpaid principal balance, the status, the probability default of the model, and delinquency. The approach that we can take is that the unpaid principal balance can get paid down in equal increments. So we are always paying off, if we have 6 months, we're always paying off 1/6. So at the beginning, at the end of the first month, we have 1 minus 1/6 of the loan, and that's how much is left. In month 2, we have 100% minus 2/6. In month 3, we have 100% minus 3/6. And finally, at month 6, we have 100% minus 6/6, meaning that we have nothing left to pay off. So that's how we simulate the payments. And if you know how to amortize loans, then you know that this is an approximation. But that's fine. We don't have to go into, we don't have to make loan tables in order to simulate our world of loans. We're focusing more on the default aspect. We also have the status. We're going to leave it active, and the probability of default is going to always be the original probability of default because we don't have defaulting happening. And then our delinquency is we were always 0 months delinquent, and at the end of the loop, the final status is that our loan is complete. And so there we are. That is our universe, and let's give it a run. Oh wait, I have to change SimPD again. Actually, wait, let's come back up just a little bit of a change. Let's make SimPD equal to 0.25. There we are. And now I'm going to use SimPD everywhere. All right, so the SimPD is now our PD at origination. Okay. And now our loan has these things, has all these aspects. Let me come over here and let's enjoy looking at them. So if I look at unpaid principal balance, there we are. There's our dates, and then for those dates, there's the matching fraction of the loan. So at month 6, there's only half left. At month 12, 11, 10, at month 9, there's only a quarter left, and so on. And at month 12, out of 12, there's nothing left. Okay. So now let's take a look at the homework. Store the simulated histories in a list. Oh, that's not bad. Since we've already done the hard part together, this homework is a piece of cake. We just have to take the unpaid principal balance, the status, the PD, and the delinquency. In fact, I'm going to steal this. And I'll come over here. I'll just paste these below just to have them to copy. It's just temporary. I'm going to delete it in a moment. But I'll just have UPB and status and my probability of default according to the model, and finally delinquency. I will delete everything else. All right. So homework 4.2. Store 1,000 simulated loan histories in a list of lists. Okay, now it's getting a little harder. Now we're going to do this over and over again. And here is the loop that is looping for 1000. Notice how there's no loop index because you don't really need it. That's just a little bit of if you don't use the actual loop variable, you could put an underscore so the letter I isn't wasted. We don't actually have to do for I in range if we're not using I. So we're just appending all the loans. So it looks like we're just doing this over and over again. We could steal this machinery and put this inside of the loop. I'm making some room, a lot of room, so it's really, really clear. I'm pasting. I'm going to tab. In this example, we're simulating history where there was never any default, so this is always false. And now, the only thing that was really random was the loan term. So let me get some of those ingredients. I'm coming up to get the ingredients for our loan. So coming up, 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 we can simulate our term. Where are we? I'm coming way up. There we are. I could simulate the size of the loan. And I could go up further because this was simulating many, but we're doing it one at a time in this case. There we are. So sim size. I can grab the size and I could grab the term. Let's come back with the term. So there was the term, and now I'm going all the way back down. And in fact, this is something you're not supposed to do. Me going up and down like this, what I should do is I could come over here and I should use the hyperlinks. So we are at simulating history. We're at 4.2. There we are. So I just clicked on homework 4.2. And I'm going to grab the term right over there. So there's my sim term. Let me make some room. And I'll paste. And I'll grab sim term. So sim term is equal to that. Okay. And then I need my probability default. And that was from the rate. So I'll have to go grab the rate. I'll come all the way back to homework 1. And where's the rate? There we are, sim rate. I'll steal that, come back to the hyperlink, down to homework 4.1. There we are, there's our rate. And then my PD, sim PD, was equal to the rate squared. And I think that gets us, oh, and we also need an origination date. All right, let's go back up. And let's get an origination date. I'll steal all of this work. And I will come back down. Okay, and I'm going to highlight it all, hit Shift Tab to align it to the left, and then Tab again to have it indented. And then I need to make sure that my terminology is matching. So sim data ridge, great. And now I think I have it. So as I look through this, I have my origination date, my term, I could highlight that, my simulate probably the default, and we are good. The only other thing is that I need to set my choices to just 6 or 12 because I didn't fully develop 8. If you remember in the example above when I made the default curves, I didn't do anything for an 8-month loan. So I just have to delete 8 because I didn't fully develop that. Okay, let's give this a run and see if it works. Awesome. Okay, so we've now built a universe. I don't quite, if I just show loans, it could be pretty big. Yeah, I was worried about that. Let me not do that. I'm going to cancel that. Okay, so we can't really look. Let's look at loans. Okay. So there's loans 1, and here are the dates from it. I think I've made them. So loan I. So loans.append. I now need to capture everything into loan I. I forgot a step. I forgot the work that we did over here. So here is loan I. I will take this and I will put it right over here. There's loan I. So loan I is all of the information retrieved from this simulation. And then I put that into the list. Okay. So there is our collection of loans. Are there any questions at this point? All right. So that's quite a run. Let's take a 5-minute break. And when we come back, I'll offer a little bit more of a thematic impression. I'm worried that I'm overwhelming with too much code. So well, let's take a 5-minute break. And at 2:20, we'll come back and I'll show you some more thematic interpretations other than code. So I'll see you back at 2:20. Okay, we're back. And as promised, let's step away from coding for a little bit and just talk about some ideas. So what happens is that when you have a whole body of loans, they can develop over time. So the word for that is developing, when the probability default gets better or worse, usually worse, because you leave it as it is, but you note everything that goes bad and you think, oh, things are worse. There's a higher probability of defaulting. And there's a couple of ways in which this takes shape. One is that you have what we all know is transition matrices. You have the states in a previous period, and you have the states now. And so if you have a whole bunch of loans, you could have them be rated. Let's say they were like, actually, let's do this. Let's imagine that our data set is students. And you have A students, and you have some B students, and some C students, and some B students, and C students. And that was last semester. And then next semester, they can have different ratings. And we can have something like this. And then from this, you try to learn what tends to happen. And what you do is you fill out a table that has the counts of where everything came from and where it went to. So we had 2 A's and they went to A, and that was it. None of the A's went anywhere else. We had 2 B's, and one of them went to A and the other went to C. And we had 2 C's and they stayed at C. And we can have our total over here. We can just note our total. We had 2 A's, we had 2 B's, and we had 2 C's. And so to make these be probabilities, we divide everything by its row total. So 100% of our A's stayed at A, and 50% of our B's went to A, and 50% went to C, and 100% stayed. And lastly, what you could do is like, fine, you learned that from a previous semester, but let's say in a future semester, you have a new batch of students, and you have 100 students, and made up of 50 A's, 20 B's, and 30 C's. And so what's going to happen is at the end, your next semester, where are all of these students going to end up, these 100 students? Well, the 50 A's will stay at A. Of the 20 B's, you'll get 10 of them going to A. So you end up with 60 A's. Nobody's going to go to B, and 10 of the B's are going to go to C, and the 30 of C's are going to stay at C. So you'll have 40 C's. And now you can see that how you can migrate from one setting to another by using this transition matrix. So we know this idea, but here's the trick. When we end up with that data, how do we get from this concept, which is very understandable, how do we get there from this data set? It's an adventure, it's a ride. And it's a ride because right now we're simulating the data, and the data have histories. And first we need to align them to be into objects that we can just have one by one. And then we need to get into a database so that we can give to analysts that work with databases, because we don't want our analysts to necessarily be programmers. And if they are, great, but if they aren't, we want to give them just a good old SQL database to let them do their analytics. And then that introduces the challenge. That introduces the challenge of how do we get from SQL to a transition matrix. So it's you see how these things that they sort of they explode when you apply them. And so that's where we're headed right now. And let's jump back in and do another round for as long as everybody lasts. And we'll see if we can make it to the SQL stage and see if we can have a transition matrix result. And then we will have lived the path from having our data as objects, because when there are objects, you can have them be flexible. You can have a history as well as a single data point. For example, you wouldn't be able to squeeze in all the things we've made into an Excel sheet, because you could have for some loan, you could have here's its date of origination, here's its probability default at origination, here's the rate. But then where do you put the history? The history is an entire column, so you can't fit it into one little row, one little single row. So it gets messy. You would need a three-dimensional Excel sheet. And there are companies that actually do that, but the better way is to do what we're doing, to keep it as an object that could do anything, and then get your object into a nice flat file SQL database for those who want to work with databases. And let's go ahead and give that a go. So I will come back to sharing my screen, and where are we? Here we are. We have simulated our loans. So what did we do? We had a term, a rate, and a PD. And into the loan, we stored, in fact, we could actually store more. So every single loan has a term, and it has a rate, and it has its probability of default, and it has its date of origination. Okay, and so every single loan has this collection of things. And as you saw, some of them are dictionaries indexed by date, and others are just data points. And because you have both of them, you can't fit them nicely on a spreadsheet. And so let's run this again. Now that's run. And let's look at just the first one. So, sorry, where'd it go? Loan 0. So I have my my date of origination. I have my term. I have my probability of default. I mean, I have my interest rate, 16%, and my probability default, 2%. And then I have my unpaid principal balance indexed by time. And that's a lot of time, though. Where's my sim term? Should be between 6 and 12. So my sim term here was 6. And so I should have 6 time periods. There we are. So the loan was born on, we can see the loan is, there might be an error because I see that my date of origination is 2012 October. So October 2012 is when this was born. And there it is. And then what I want to do is I want to evolve the loan each period. So then I add 1 month to it and record my data. Oh, I get it. Okay. And I think I need to clear these out. I need to refresh them every single time. Let me come back up. Maybe I did that. Aha, here we are. We just made this a little messy. We need to be resetting these. Let me grab this, and on every loop, let's make these nice and fresh versions of themselves. Okay, so now we have nice, fresh, empty dictionaries on each loop. Let's try this one. Okay. And now let's look at loan 0. Okay, that looks like a much more reasonable size. And now this loan was born on May of 2017. And then there we are. And now its history begins 1 month. So June, July, August, September, and it made it all the way till December. Actually, it's a 12-month loan, so it goes all the way until May of 2018. Great. And there it is getting paid down incrementally. So that all makes sense. And it's active the whole time until the last period where it's marked complete. And the probability of default remains constant because the customer always paid and there was always 0 delinquency. Okay. And you see how this doesn't fit in a spreadsheet. Like if it was just these 4 points, if it was just like, how long is the loan? What's the interest rate? What's the probability of default? Sure, you could put those in a table in an Excel sheet, but you can't fit these into a single cell. I mean, you can if you sort of stack them in there as a gigantic text string, but that's no fun. You can't really refer to the parts all that easily. So there we are. Okay. Now we have a little bit of a challenge. And it's a healthy challenge. It's a good challenge for us to feel because this is it's a healthy challenge for us to feel because this is what our world of loans is. Like you want to know the universe that you're responsible for. If you're a risk manager, this is it. This is your world. If you're a risk manager at this lending company. And so we have to simulate a richer data set that includes the defaulting. And what we're going to do is we're going to have a little print machinery here. So I'm not going to review this. It's because it's just a little bit of Python work. And it's just purely about Python. You could look this up. It's just this format string tells you how many spaces to allocate to everything. And this just makes a nice print. So I made this little thing called print it. And then we can have our default is equal to false as before. This is what we did the last time. And this time, if we can just test our printing. So we're going to test our printout for the no default case. And this is beautiful, right? Notice how before it was a fight. We had to really read this all out, but now we have a nice display. We turn it into a table. We use this little print it thing that I made. And now we're printing on each loop. And I have the loop broken into 2. I broke this into 2 in order to show us something. We can break our loop from 1 until the term of the loan. So if we had a 6-month loan, we would go 1, 2, 3, 4, 5, 6. If we had a 12-month loan, we would go from 1 to 12. But if we, yes, and so this second part does nothing. This does absolutely nothing. It's just a demonstration for learning purposes. I'm going up from 1 to a time, and then I'm breaking it to go from that time to that time, so I don't really get anywhere. But later, instead of having this be, I could have put another number in here. I could have put 3 in here. Then I would go from 1 to 3, and then I would go from 3, from 1 up to, but not including 3, and then I could go from 3 up until the end. So I've broken up the loop from 1 to n into 2 parts where I could split it in the middle. And the reason I've done this is because we're going to simulate a default. We're going to turn this to true. And then we're going to have 2 types of loops. We're going to have the first loop where we're getting paid, and then the loop after that. Okay. So here we are. Here's the setup of a universe. We have the unpaid principal balance, status, PD, model delinquency, unpaid principal balance, and all of that is good. And then this time our default is going to be true. We're going to simulate a default time. And later we're going to use better machinery for this, but for now we're just picking 8. So we're just saying you're going to default to time 8. And I guess if we do that, we have to set our term. Oh, we simulated an 8-month loan. Okay. So, and we simulated an interest rate of 30%. Okay, so having just made this up, we've just totally made this up. We are going to default. We're going to default at time 8, and we have an 8-month loan, and the interest rate is 30%. So we can now take this heavier code. It's getting heavier. So we're looping until default. So we go from the same thing we did before up until the default time. And the default time we set here is 8. And then from the default time up until the default time plus 1. So that means pretty much nothing happens. We would be printing. And then after the default, we continue doing more. Okay, so let me dig in. This happens in layers. So we have the probability of default now is going to change. Now we have a little mini model. This is not robust modeling. It's just a mini model to make reasonable data. So we're going to take the probability default and we're going to take the root of it. So if you're 1 month late, we'll take the square root. If you're 2 months late, we'll take the cubic root. Well, we're going to inflate the probability default by raising it to a fractional power. So every month you're late, the probability of default goes up. And that's just the model. And the details are that right over here, we're looping in time. And so we're going to take the current time minus the default time and add to that. So if you're at the default time, you're going to have some probability default. And then the 1 month after. So if I was if I was in month 5 and the default time was month 3, then 5 minus 3 would be 2. I would be 2 months into defaulting. And then I'm going to add 2 to this. That's just the model. That's to get it to a higher power. And that's yes, that's just the game there. Okay. And then after, oh, I see. This one is, and this is what happens at the time period of default. So we have before default, we have at default, and we have after default. After default, we can either give up on the loan, that's called a write-off, or we can have the loan paid off, that's called complete. And what's happening is that we are going to simulate whether or not the loan heals. And so we have our, we're going to keep on adding delinquencies. and the probability of default is going to get worse and worse. And then the status, if the delinquency is equal to 3, we're going to put it in write-off. Okay, and there's no healing just yet. So one more time, hard stuff here, right? That we've been working. This is the peak of difficulty. This is what we have been fighting for. So we're warm. We've looked at the code, and let's just fight one more time, because this is our payoff. So when we default, we're going to loop up until the default date, just like usual. On the default date, we're going to leave almost everything the same, right? The unpaid principal balance is still the same unpaid principal balance that it usually is. I'm sorry, the unpaid principal balance is the previous month's unpaid principal balance, because they didn't pay, right? So how much is outstanding? The same as before, because they didn't pay anything. The delinquency is still 0. This is why we need the special case where we're breaking it up into 3. We're breaking up to before, at, and after. Why do we have to do at? Why is it before, at, and after, and not just before and after? Because on the first day that you are late to a payment, you are 0 months late, but there's a problem. You're still in default. You missed the payment. It's 1 day late. We know that you've missed it. We know that, oh, whoa, something's wrong. This could be a person who's not going to be paying us eventually. So you are 0 months late when you are 1 day late. But at 1 day late, we have to change our model. Our model probability default has to get smarter. And so we add, even though you are 0 months late, we're going to add 2 to this and take the square root of your probability default in order to inflate it. So if your probability default was 1/4, it's now going to become 1/2. And that's how we move things forward. Okay, so let's give these a run. So I'll run over here, I'll run over here, I'll run over there, and here's our view of it. So we went up until month 8, and there was only 1/8 of a payment left at 1/8 at time 8. But that 1/8 of a payment wasn't made. And so our probability default had to go up at that period. And so we took something like the square root of 8%, and that moved us up to 28%. And then we keep on square rooting or taking different modeling roots to move this probability higher and higher. So notice how this is increasing. And in a sense, it didn't increase fast enough, because if on month 3, this person did default, then maybe this should say 100%. Like for this loan, we should say 100%. But maybe if all loans like this, only 60% of them default, then maybe this 0.6 is okay. And now you know what it's like to drill into the data set. Now, if you had this in a big SQL data table, in a big SQL database, you would explore this. You would say, okay, look at that. When our loans are 3 months late and it's this kind of loan, we have a 60% probability of loan. Let's query for all of the loans that are 3 months delinquent when they were 8-month loans and they were from this location, do 60% of them default? And if the answer is 80% of them default, then wow, our analytics for modeling probability default, they aren't sufficient. Of course, my analytics right here is just a made up square rooting technique. So the actual company would have a more sophisticated model, but it doesn't matter what the model is. The point is you have this number 0.6, and you compare this 0.6 to what's happening with your data. Okay. So now we have to simulate the default and store the history. So for 1,000 loans, simulate whether or not default occurs. then simulate the corresponding history and store it in a list. Okay, now that's getting intimidating, but it's not too bad. We've done the work. The work was understanding it. Now we can just grab it. So we can come over to the code that we made before. Let's come back up. Here's all the work that we've done. And you can also see why there's a course for all this. So all this happens, week by week, where we're taking weeks of work and we're squishing it to our build it in the day seminar. But the course gives you the best of all worlds. You can see it all in one day, but you also have 12 weeks to work through it. So here is this universe of loans. I will come back down to our actually wait, I'm going to use the table on the left. I'm going to select this. And there we are. There is our table of loans. And our default was just yes. But we know how to change that. We could have np.random.choice and true, false. Okay. And then all of this work was the true work. So so then below that, I could have if. Right, so if we defaulted, then we're going to do some stuff. And then else, we're going to do all the stuff that we did before. So all of this is the else condition. And now what we need is we need to get our work over here for the default. Now, I think I may have put too much stuff. I could take all this out. Let's grab this. This belongs up here. I'm going to take this and pull it up here. I'll hit Shift Tab to move it back. All right, yes. So there's our loan. We have our fresh loan. We have all of our dictionaries empty. We've simulated whether or not defaults, the term, and there we are. And I am worried. Maybe I just need to put the number 1 there, or I'm worried. I don't know why I have that little error there. I'm just looking. So I have if, and then it should like my else. Oh, good, it does. Okay, great. Okay, so now we just have to put the default work in here. And that's okay. We know how to do that. Let's come back up because it's given to us. Here it is. Here is the default work. So I will take all of this. And put it right over here. And I think I need to tab it all. So I'll come over here and 1 tab. Okay. And then this part, this collector, this big collector here that collected everything, it's going to work for both cases. So we can test it. I could take this and I could pull it up here temporarily. I'm pulling up this thing that collected everything. It's collecting our delinquency, our PD model, the status, the unpaid principal balance. We've got our whole universe all collected. And I'm going to take this and I'm going to cut it. And I'm going to put it over here outside of the conditional, because this one happens for both of them. So I'll take this and I'll just increment it back once. And now we have it. We have our loans defaulted, assessed in both cases. Okay, so I will hit shift return. I'll run this. Okay, so this is good, except when I stole that code, I stole the print function, and now I'm printing thousands of times. That's bad. That's going to slow down my computer. In fact, okay, so I have to kill off the print it. There we are. No print its. Okay, let's run that again. Great. And let's just take a peek at loans 1 or 0. Okay. We've captured a universe. And this was an interesting loan. Look at that. It defaulted in, well, it defaulted eventually. I don't know when it defaulted, but it defaulted around here. And we could see the probability defaults increasing. We could see the delinquency increasing. We have real history happening. Okay, let me show you what happens with the rest of the code. And maybe this is a good amount for this time. In the applied coding class, they will do another round of this. I'm worried that I'm killing everybody. It's just so much detail. In the future, I will include more thematic breaks to mix this up between code and ideas. And I do apologize. I was just stepping in because we rescheduled. But this is also a lesson to me. So the next time I present this, I will have more themes to take breaks from the coding, since this is so code heavy. And if you have any suggestions, don't be shy. Feel free to email me. But let me show you how the rest of the code works, because you have this and you could study it when you take a break and come back after you recover from from a 2-hour injection. Although on the upside, this is what it takes. This is the build it in the day battlefield. But let me show you. So the next steps are to simulate this with recovery. And that just changes the feel of this a little bit. And it's just another condition that we have to make another random draw to see when the loan recovers, because the loan is going to, people do recover, right? People miss 1-month payments all the time. And they even miss 2 months. By the time they miss 3 months, you're pretty sure they aren't going to pay you back. So you make a little model for the probability of default, and then you have to have that case. And so this code includes the recovery. And then after that, you have it. And then the next step is to take these lists and make them objects, just because that's what's natural. In fact, the list kind of is an object. A list is a pointer to things that are of different shapes. But if you have the same thing, the same shape happening over and over again in your list, then that list is pretty much just a homemade natural pointer, a homemade object. I'll say this one more time a different way. An array of pointers to objects with the same shape in memory is basically an object, your homemade object, where that same shape is your object type, and the pointer is just an array of those, and the array is an array of those objects, and the list is an array of those objects. So we have basically already made an object when we made that list before. Now what we're going to do is we're going to make it official. We're going to make a loan class and populate the loan class. And then after you make a loan class, just pretty much just moving your list from the list that it was to a class, you then need to do one more step, depending upon what kind of work culture that you're at. If you're at a fancy place, maybe a hedge fund that works all in code, you can stay in code. If you're at most organizations, you're going to want to get this into a database so you can give it to a data analyst or a business intelligence analyst. And so what you'll do is you'll loop through the objects and populate flat files for everything. And you'll have to have 2 different files. You have to have one, which is the nice Excel sheet for the loans, the name, the age of the name, the industry, the probability of default at origination, the rate that's charged, all those point values, but not the histories. The histories have to go into another database that covers time. And so you'll make two databases here, the origination database and the post-origination database that goes by time. And then finally, you'll be able to build a transition matrix out of SQL code. And that code is over here to show you how to do it. And then you could visualize and play around a little further. And so there it is. That is a tour of what it is to build the infrastructure for a lending company in a day. Are there any questions that I could answer for everybody? All right. Well, I hope you learned a lot. I hope it's an exciting experience. Well, maybe it's too much code to be exciting, but you understand. But hopefully you really have a good overview, and you could study this at your own time, reach out with questions, and you could really come to master the building of the infrastructure for a lending company. Okay, with that, I leave you to your Fridays. Next Friday's presentation will be a little bit lighter and more thematic, and so I hope you'll come back to join us. And see you all guys. See you guys later. Bye bye, everybody.